A split second, the Big Bang, and the whole universe was born.
In the blink of an eye, literally, so much can happen that it would blow your mind.
How did we get here? And what is the universe made of?
The secret of creation, the secret of everything, is locked in that first second.
Technology stands on the brink of revealing what happened in the most important second of all time. In the beginning, there is nothing. No matter, no energy, not even empty space, because space itself doesn't exist. No time passes, because there's no such thing as time. From nowhere appears a fireball smaller than an atom. 10 trillion times hotter than the core of the sun. Everything that will become the universe explodes from a point millions of times smaller than a pinprick. Time begins. In 1 second, the blueprint for the entire cosmos is written. How it happened is the biggest mystery of all. Professor Lawrence Krauss has devoted his career to studying the first second after the Big Bang.
If we want to really understand our place in the universe, we have to go back to the very beginning and understand how it all came together.
Looking back to the instant of creation is a new idea. The theory of the Big Bang is widely accepted, but the concept is less than a century old.
But one of the things we have to put in perspective is how recent our understanding of the universe is. 80 years ago, the conventional wisdom in science was that the universe was static and eternal, had been around forever.
But this changes in 1929. At California's Mount Wilson Observatory, Edwin Hubble studies the light from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light waves stretch the more they travel, and stretching changes their wavelength. The same principle applies to sound waves. As a train approaches, the whistle's pitch rises. When it passes, the pitch lowers. As the train recedes, each sound wave has to travel farther than the last to reach your ear. The sound waves stretch, lowering the pitch. Something similar happens with light waves. If a galaxy is moving away from us, its light waves stretch, becoming longer and redder. It's called red shifting.
When we look at visible light, there's red at one end of the spectrum and blue at the other. Red radiation is the long wavelength radiation of visible light, whereas blue radiation is the short wavelengths. And as we look at the universe, we see the radiation from distant stars literally stretching so that the light gets redder. And the farther away we look, the redder the light is.
Galaxies around us have shifted to this red light.
We look out in all directions at distant galaxies. They're all moving away from us.
Nearly all galaxies are receding at 1,000,000 miles an hour. If galaxies are speeding away from each other, at some point, they must have all been together. The universe is expanding outward from a single point. It's the first evidence that the universe had a beginning. Hubble's findings lead to a radical concept: the Big Bang theory. Scientists believe that in the first second after the Big Bang, the building blocks were created for every star and planet in the cosmos. To prove it, they first need a new way to tell time.
We are thinking of fractions of time smaller than we think about in any other area of human activity, and smaller fractions of time than a race car or a sprinter or anything else. And what we've learned is that more can happen in a fraction of a second, in a blink of an eye, than you can imagine. It would just blow your mind.
Hours, minutes, and seconds are the basis of modern life. But events after the Big Bang happen in fragments of time far smaller than a second. To analyze what happens, scientists use a new measure of time called Planck time. 1 Planck time equals 10 to the minus 43 seconds. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy, all the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal, a beautiful symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as super-hot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red, then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called cosmic microwave background radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next. A few beats of Planck time tick by on our cosmic clock, and the fireball universe is transformed. One instant, the universe is billions of times smaller than an atom. The next, it inflates to the size of a baseball, growing more in this moment than in all the 13.7 billion years to come. Scientists call this rapid expansion inflation. And the evidence survives in the cosmic radiation left over from the Big Bang. Like static on your television, this cosmic radiation seems so constant and so even, it presents scientists with a puzzle.
When we measure the cosmic microwave background in that direction, its temperature is identical to its temperature in that direction. It's the same everywhere.
The only explanation is the universe inflates countless times faster than the speed of light. Inflation expands the fireball universe evenly, like a balloon blowing up, with a phenomenal breath of energy.
I try to imagine compressing a spring. I push it closer and closer and closer together so it's smaller and smaller and smaller, and I've stored a tremendous amount of energy in that spring, and when I let it go, it bursts out. And that stored energy drove an exponential expansion of space.
But if the entire universe is uniform from the first second after the Big Bang onward, how did the galaxies form? Planets and stars begin as clusters of particles. Over time, these particles of matter clump together under the force of gravity to form a dense mass. Earth began as a ball of particles that clumped together through friction and gravity. The sun that sustains life on Earth started out as a cloud of gas and dust. How did these clusters form in the first place? The early universe should be lumpy, not even. To link the formation of stars and planets all the way back to the first second after the Big Bang, NASA scientists like David Spergel developed the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite mission to measure the temperature of cosmic radiation in more detail than ever before.
While this radiation is everywhere, it's very faint. And to observe it in great detail across the whole sky, you want to get away from the Earth and any interfering sources of radiation.
7, igniters armed, green board, 5, 4,
NASA launches the probe in 2001.
main engine start, and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
It could produce the best ever snapshot of the universe in its first second.
The launch was incredibly exciting, tense, An exciting moment to see it go up and then realize it was working.
WMAP sits 1 million miles from Earth. It's so sensitive, it can measure the temperature of cosmic radiation within 1/1,000,000th of a degree. For 5 years, WMAP analyzes the sky in minute detail.
It sits there with the Earth and Sun always behind it, staring out into space. The satellite's spinning very rapidly. It covers about a third of the sky every hour, spinning and making maps of the leftover radiation.
WMAP tracks the Earth as it orbits the Sun and scans the temperature of the whole sky. It generates detailed temperature maps like this one, and it reveals something remarkable. The blue and red patches on this map of the entire sky are tiny ripples in temperature.
The little blue regions represent regions that are a few tens of thousands of degrees colder. Red regions are a little bit hotter, so you're seeing tiny variations in temperature across the sky.
WMAP looks back over 13 billion years. As the universe evolves, these tiny ripples develop into clusters of particles that get bigger and bigger under the force of gravity, becoming just dense enough to trigger stars and galaxies to form.
I mean, it really was what I think we all dream of when we go into science. Looking at things that no one's looked at before, learning really exciting things about fundamental questions. Questions like, what's the universe made of? What happened in its first moments?
This is a map of how the universe looked in the first second after the Big Bang. The template for today's vast cosmos.
When the picture of the cosmic microwave background radiation first came out, the press said, the face of God. Well, let's be real. It's not the face of God. What it really is a baby picture of the infant universe. So the discovery of the cosmic microwave background radiation ranks as one of the greatest discoveries in all of science.
Less than 1/1,000,000th of a second after the Big Bang, the fireball universe rapidly expands. Now an ultra-hot globe big enough to sit in the palm of your hand, the universe is seething with energy and radiation. But as the palm-sized universe expands and cools, something new starts to form. Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists, until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. We're only a fragment of a second into our journey. The first particles of matter appear. The universe is 1,000,000 times hotter than at the core of the sun, still far too hot for particles of matter to bond and form atoms. Scientists face a puzzle. What is this early state of matter like? And how does it become the protons and neutrons that form every atom in the universe?
Atoms were impossible. Think of putting an ice cube in a steam bath. The ice cube would melt immediately. You cannot have ice cubes in a steam bath.
You can see the proof in a block of ice. When water is cold enough, it's a solid. Warm it, and you get a liquid. Heat liquid water, and it boils away into a gas, water vapor. Superheat the gas, and the energy pumped in rips the atoms apart. Likewise, the universe in the first second is so hot, only the building blocks of atoms can exist.
If you were to journey into the early seconds of the universe, literally you would disintegrate. You would literally fall apart, and even the debris, the nuclei of your bodies, they too would fly apart into subatomic particles. There would be nothing left of your body.
There's only one way to see these super hot building blocks of matter in the first second after the Big Bang. Scientists must recreate conditions of the Big Bang itself.
The inside of a star is measured in tens of millions of degrees, but the Big Bang was measured in trillions upon trillions of degrees. So we have no way to simulate the instant of creation other than with a particle accelerator. By slamming protons into other protons, we can create temperatures not seen since the beginning of the universe itself. So particle accelerators are the only game in town when you talk about simulating Genesis.
This is Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC, a 2.5-mile ring designed to smash the nuclei of gold atoms at nearly the speed of light.
With the particle accelerator, you slam subatomic particles together. As a consequence, we get a tremendous shower of debris, and then we want to make sense out of it. We want to know what's inside that collision.
The energy of the collision is colossal. On a small scale, it reproduces the embryonic universe in the first second. How? By ripping nuclei into the protons and neutrons they're made from. The energy is even enough to rip the protons and neutrons apart. Inside, scientists discover the building blocks of matter, tiny particles called quarks. But they're so small and move so fast, they're hard to track. If scientists can figure out how quarks behave, they'll unlock the secret of matter itself. What they find could revolutionize medicine and relaunch the space program. The project starts in 2000. Colliding nuclei creates a chaotic spray of particles. It takes 5 years to analyze the data. The results come in 2005. They're shocking.
We were expecting to find a gas when we slammed gold nuclei into each other. So the shock was, it wasn't a gas at all. We found that it's more like a liquid. So this came quite a shock, because now when we begin to simulate the early universe, we have to get rid of this mental picture of a gas of subatomic particles. Now we know it's more like a liquid, literally like a soup.
When matter first appears in the universe, the quarks are so dense and so energized that the entire universe is like a liquid. The universe went from a glowing ball of energy to quark soup in less than a blink of an eye. The liquid universe is hot, dense, and violent, flooded with tiny particles in constant vigorous interaction. As our cosmic clock reaches a millionth of a second, the universe continues to expand and cool. It grows from the size of a baseball to the size of our solar system. Matter has materialized from pure energy. Without matter, none of us would be here. And in that first second, that very nearly happens. Something comes close to destroying all matter in the universe. Armageddon is brewing. A split second after the Big Bang, and the universe is flooded with the building blocks of atoms. These tiny particles of matter must survive in a battleground. Everything around us is made of matter formed from the energy released by the Big Bang. Every molecule, every atom, every quark. How we end up with a universe that consists of so much matter is one of our biggest questions. The particle accelerator may reveal the answer. When the first second is recreated, two types of matter are produced in equal parts. One is the type of matter we see around us. The other is its opposite, antimatter. Dr. Tara Shears explains they're two sides of the same coin.
This apple is made of matter. We know that every matter particle in the universe has an antimatter partner that was created in the Big Bang. Now, antimatter looks similar to normal matter, but not quite. In fact, it looks like the mirror reflection of matter. So an anti-apple looks like this.
If the universe was made of antimatter, it would essentially look identical to how it looks today. You and I would be made of antimatter, and anti-lovers would sit in anti-cars looking up at an anti-moon at night making anti-love, and it would be largely the same.
But matter and antimatter are mortal enemies. They can't coexist.
When we have a matter particle meeting an antimatter particle of the same type, then they annihilate, they explode together, they destroy each other. All the energy that the matter and antimatter particle have goes into one large explosion of huge, tremendous energy.
Fractions of a second after the Big Bang and the future of the universe is at stake, matter and antimatter are locked in a battle to the death. A millionth of a second after the Big Bang, and a battle rages. When matter and antimatter clash, the result is explosive. Just one apple-sized clump of matter hitting its antimatter equivalent would release as much energy as a 10-megaton nuclear bomb.
If you could go back to the really early universe just after the Big Bang, you'd find yourself in this seething mass of matter and antimatter annihilating each other. You'd find yourself in the middle of this cosmic battle between both sides, caught in the crossfire, if you like.
With all the particles in a super-dense liquid state, matter and antimatter quickly meet and destroy each other. Since they're created in equal numbers, and every matter particle that hits an antiparticle is annihilated, all matter should be destroyed as soon as it's created.
All the matter would have eventually found the antimatter, and they would have annihilated, producing pure radiation. And we'd now have a universe. I was going to say we'd now be living in a universe of pure radiation, but we wouldn't be living in such a universe because we wouldn't be here. There'd be nothing but radiation.
But the universe is full of matter. How did it defeat antimatter? It's one of science's great mysteries. One theory is that antimatter is less stable and decays more quickly, creating a tiny imbalance between matter and antimatter. This tiny imbalance eventually allows matter to overwhelm antimatter. Whatever the truth, something happens just after the Big Bang that tips the balance in favor of matter.
And the whole battle stopped at that point, and what was left was a very small amount of matter. And it's that small amount of matter that makes the universe that we live in now. That means that we're the leftovers of this battle. We're the dregs. We're what's left when everybody else had finished.
The dregs go on to form everything around us. From the ground beneath our feet to the most distant galaxy. As the cosmic clock nears the end of the first second, nature's four forces have split off from the single superforce. The winner of the matter and antimatter war has been decided, and the subtle ripples in temperature that stretch across the universe mean that over the next billion years, gravity gathers clumps of matter to form galaxies. But one mystery remains, and it's a big one. We know how the building blocks of matter form, but we don't know what gives everything in the universe substance. We know so much about the first second, but a piece of the puzzle is missing. What gives everything in the universe mass? Mass makes it tough to get something moving, and makes it hard to stop. When we're pulled down to Earth, gravity is acting on our mass. On the Moon, gravity is weaker, so astronauts move slower, but their mass is the same as back on Earth. Even if an object weighs nothing, it still has mass. Something must have been created in the first second to give particles mass, but scientists haven't found it.
We have this hole. We have this missing piece. The centerpiece of this whole picture is what happened during that first second of creation. If you know that, then you can, quote, read the mind of God, as Albert Einstein used to say.
Mass is the very backbone of life.
If there were no mass, the universe would consist entirely of radiation, and nothing could bind together to form objects like you or I, or any of the things that appears to make the universe interesting. It would be a diffuse universe full of radiation, but very, very boring.
Discover how mass develops in the first second, and you uncover the root of life. If scientists can't find what gives particles their mass, that first second will remain an enigma. Our journey is almost finished, but a piece of the puzzle is missing, and it stumped scientists for decades. Then in 1964, at Britain's University of Edinburgh, physicist Peter Higgs comes up with a groundbreaking theory. He suggests an invisible force field sweeps across the universe in the first second, giving particles their mass. It's become known as the Higgs field. When particles interact with it, they gain mass.
For example, if I take a car and that's run out of gas and I push it on the road, eventually I can push it and I can move it along. But if it runs into the mud, if I try and push it, it will suddenly seem heavier. I can't push it as hard. It'll act as if it's heavier. Well, we think that particles have mass for a similar reason. There's this Higgs field, and some particles interact with it more strongly than others. And the particles that interacted with it less strongly are easier to push, and therefore behave as if they're lighter. The particles that interact with it more strongly are harder to move and act as if they're heavier.
Like mud, the Higgs field sticks to everything. When particles enter the field, they gain mass. The more contact with the field, the more mass they gain. Scientists believe the Higgs field is carried by its own special particle. Journalists call it the God particle. Scientists call it the Higgs boson. They think identifying this particle could reveal how we got here. The math is good, but no particle accelerator was powerful enough to find the Higgs boson. Until now. Deep beneath the countryside in Geneva, Switzerland, is mankind's most expensive experiment, the Large Hadron Collider, or LHC. The world's biggest particle accelerator and the best shot at finding the missing Higgs.
We've got to see if the Higgs particle really exists. And that's why we have to build these mammoth accelerators, to see if we can understand the mechanism responsible for the existence of everything we think of as solid and heavy in the universe today.
It cost $10 billion, took 14 years to build, and involves the work of 7,000 scientists. This year, they switch it on. On a small scale, it will recreate conditions last seen over 13.7 billion years ago. An explosion so powerful, it will echo the Big Bang itself. If it works, scientists like David Evans could solve the last mysteries of matter.
Because we're pushing the frontiers of science, we have to also push the frontiers of technology. It is, as well as probably the biggest machine in the world, it is certainly the most complex machine in the world.
Over 300 feet underground runs a 16-mile circular pipe. Inside, two beams of protons, thinner than a human hair, are accelerated to almost the speed of light, 186,000 miles per second. The LHC will smash particles together 7 times harder than any other accelerator. 300 trillion protons fly around the pipe in opposite directions and collide in the heart of enormous detectors. Lawrence Krauss inspects one of these detectors, each the size of a 5-story building.
Here we are at what's been aptly described as being one of the Gothic cathedrals of the 21st century. This monstrous structure made of thousands of tons of steel, more iron than in the Eiffel Tower, with tens of thousands of miles of wire. All of this designed by thousands of physicists from hundreds of countries, speaking dozens of different languages, with the precision of perhaps a millionth of an inch, just to detect what happens inside there.
The LHC uses 4 of these giant detectors along the beam pipe. The one they hope will find the Higgs is called Atlas. Atlas is half the length of a football field and weighs as much as a nuclear sub. It can detect 1 billion collisions per second. When the protons collide, the impact is so titanic, in a split second, it will recreate matter as it was just after the Big Bang. A shower of fundamental particles, like quarks. Somewhere in the debris, they hope to find the elusive Higgs. But finding one particle in this firestorm is like finding a speck of gold on a beach. The Higgs is so tiny and so short-lived, the detector won't see it directly. Instead, they hope to capture the trail it leaves behind, using the most high-tech cameras in the world.
When you look at a Skyrider, you see this gigantic plume of smoke, but where's the airplane? You never see the airplane. The airplane is too small to be seen. That's how we use detectors. Detectors cannot pick up the particle itself, but it can pick up the trail left over by the subatomic particle, and looking at the trail, we can determine what kind of particle it was and how fast it was moving.
The LHC will generate more data than any other instrument on the planet.
In a single second, the amount of information that's coming out of the collisions at the LHC that will be handled by these detectors is greater than the amount of information in all the libraries in all the countries in the world.
That data may hold the secret of mass, the missing piece in the universe's first second, and the doorway to the science of the future. To process all this information, the LHC uses the world's largest network of supercomputers. Even so, the search may take years to complete, but it's worth the wait. If it succeeds, the LHC could launch a new era in science. If it fails to find the Higgs and reveal how matter gets its mass, it will leave a hole in the riddle of the first second. New theories will have to be written, and more powerful experiments built.
Hey, I'm a realist. I realize that perhaps we'll find nothing. That could create a crisis in physics. It could stagnate all of physics if all of a sudden our machines are not powerful enough to unveil the next act, the next curtain, where we look at the next stage of matter and energy.
One thing they know, the LHC will take scientists closer to the Big Bang than ever before. It will reach back 13.7 billion years to recreate the very first second of the universe, the greatest second. Our cosmic clock takes its final beat of Planck time. The universe is 1 full second old. It's about 1,000 times the size of our solar system, and flooded with particles of matter, the raw material of everything around us. The universe is cool enough for the sea of quarks to bunch in threes, forming protons and neutrons. In the saga of the universe, this first chapter set the course of history.
The first second of the universe was an incredibly exciting and important time. During that first second, all the matter in the universe was made. All of the neutrons and protons were made. All the key components to make the universe today, we think were already in place. And then everything just evolved forward.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nucleus. 300,000 years later appears the first atom. In hundreds of millions of years, matter clumps to form the first stars. And in 1 billion years, galaxies like the Milky Way. More than 9 billion years after the Big Bang, Earth is born. One Big Bang, one single second. The genesis of everything.
By the time you've got to the end of 1 second, the rest of cosmic history is prescribed, including, ultimately, the future of the universe.
More than 12 billion years after the Big Bang, humans evolve. A species with the intellect to ask, how did we get here? And what is the universe made of? This year, science moves closer to discovering the answer. And the secret will lie in the first epic second. Of all the planets we know, ours is unique. The only one with water. We take it for granted, but without this magic liquid, life couldn't exist. Where our water comes from is one of science's greatest mysteries. From deep inside the Earth to the far reaches of space, the search begins for the source of our water. Earth is the only planet in the solar system with liquid water. 330 million cubic miles of it. It covers over 70% of the planet. It even makes up about 60% of our bodies. We know a lot about water, except where it comes from.
When we think about where Earth's water came from, it's not that simple, because we think that all the building blocks of Earth were probably completely dry.
If Earth forms without water, then where do our oceans come from?
It's a bit like a crime scene. The crime occurred a long time ago and the evidence has been tampered with. So it's very much like being a detective. You've got to look back in time to try and understand what was going on 4.5 billion years ago. It's a hard problem.
For the first time, scientists from different disciplines are working together to find the origin of Earth's water. The answer has the most amazing implications.
We know of no organism that does not require liquid water to live. And therefore, when we ask, how did a planet acquire its water? In essence, we're hinting at the question of what makes a planet able to support life.
In order to unravel this mystery, we must go back in time and look for clues at the birth of the solar system. 4.6 billion years ago, our sun is a newborn star, surrounded by a vast disk of gas and dust. Over millions of years, this disk of matter condenses to form the planets. Far from the sun, it's so cold, planets like Jupiter form with icy cores. Closer to the sun, it's more than 1,000 degrees hotter than it is today. Earth forms from substances that condense at high temperatures, like rock and iron. It's too hot for water. Earth is bone dry. For scientists, one possibility is that water was delivered by comets. From the frozen wastes of our outer solar system, they're mostly ice. Toby Owen has been studying comets for over 40 years.
As soon as people figured out that comets had a huge amount of ice in them, then it seemed reasonable that comets striking the Earth would have brought that ice with them, and so that ice could have melted and produced the oceans.
For 600 million years, the early Earth is bombarded by hundreds of millions of icy comets.
Comets are very primitive bodies. That's what makes them so especially interesting. The ice in comets is ice that has been untouched since the solar system formed.
So if comets brought all of Earth's water, then the water we drink, wash, and swim in fact, the water that makes up our bodies, is older than the planet itself and is from the edge of the solar system. But the evidence is still circumstantial.
We need some clues to discover how the Earth got water. We need some clues in the water on the Earth that we can relate to other things, like comets, to see if we can decide what brought the water in.
Luckily, water contains the perfect clues. To the naked eye, water looks the same, but there are subtle differences depending on where it comes from. All water molecules are made of 1 part oxygen and 2 parts hydrogen. But the hydrogen comes in 2 forms. The bulk of hydrogen in water is normal or light, but a tiny fraction, the blue bits, are heavy hydrogen. The ratio of heavy to light tells scientists where the water comes from.
You and I, and all the animals, and all the trees, and all the oceans, and all the lakes, and the rivers on the Earth have the same ratio of heavy hydrogen to light hydrogen. That's our water. That's the water of the Earth. So the question is, what is that ratio like in the kinds of objects that could bring the water to the Earth?
To find the ratio of heavy to light hydrogen in the water on a comet, scientists need to get a sample. Easier said than done.
One of the things that made people so interested in comets is that they're completely different from anything else in the sky. Suddenly, from nowhere, this huge bright object appears and moves through the sky and then disappears again.
Because astronomers never know when they'll show up, most comets are out of reach.
You'd have to keep a spacecraft in your garage, something like that, ready to go at any minute when one of those comets appears.
But one comet has a special place in astronomers' hearts. It's not the biggest or the brightest, but it is predictable.
Halley's Comet is special because it's a big comet, and still it is one whose orbit we know. So that means we can predict when it's coming back to the Earth. We can make that prediction very well.
In 1986, Halley was once again within reach, close enough to grab a sample. For Dr. Carey Liss, just seeing Halley's Comet was the chance of a lifetime.
I actually was excited about Halley's Comet, and at 1 in the morning we were out there looking out in the sky, and I remember to this day we saw Halley's Comet really nicely, and that was very inspirational to me.
Because scientists knew where Halley would be, they could build a space probe for a rendezvous. The probe Giotto was designed to fly through Halley's tail.
One of the most exciting things that Halley gave us was not just here's a comet, here's what a comet looks like, here's the structure, but we could start doing chemistry. We could start understanding the composition of the comet.
Finally, scientists can analyze comet water and discover if it's the same as the water on Earth. On March 13th, 1986, after traveling for 8 months, Giotto enters the tail of Halley's Comet. Then a crisis. Giotto hits a large particle of dust, traveling at 42 miles per second. Communications with the probe are intermittent.
There was a tense moment there when people thought the whole thing might be lost.
32 minutes later, communications are restored. The probe samples the water vapor in Halley's tail and sends the data back to mission control. Astronomers are about to find out if the water on a comet is the same as the water on Earth. But when the results come back, the mystery only deepens.
And what we discovered, to our surprise, was that the hydrogen in the cometary water was about twice as massive as the hydrogen in water on the Earth.
With twice as much heavy hydrogen, the water on Halley's Comet is not the same as the water on Earth. While it looks, tastes, and behaves just like Earth's water, to scientists, this difference is crucial. It can only mean one thing. Comets can't have brought all of Earth's water.
Well, that's a big, exciting result. It kind of defeats this lovely idea that comets brought all the water to the Earth.
In terms of did comets bring water to the Earth, it was a revolution and a change. And that's pretty exciting.
For years, scientists thought that comets were the source of all the Earth's water. But the evidence now makes this impossible.
So that was a very exciting result because it meant that you had to have some other source of water to produce the oceans that we see. And now we were going to have to go through the excitement of trying to figure out what really happened.
In 2002, a chance discovery suggests the answer might be closer to home. When the Earth first forms 4.5 billion years ago, it's too hot to form with water. But the planet has water now. If it wasn't delivered by comets, then has it been here all along? To find out where the water comes from, Professor Stephen Moyges is looking for clues to when it first appears. As a geologist, he uncovers the planet's past by looking at its rocks. But the past has a big hole. It's called the Hadean, or Dark Period, because nobody knows anything about it.
The problem of the first 500 million years of Earth history for geologists has always been that you have a nightmare scenario where you don't have any rocks or minerals to investigate.
It's thought early Earth is a fireball of molten rock, but with no evidence from this time, it's just a theory. Then in 2002, Moyges makes an earth-shaking discovery: the oldest mineral sample ever found on our planet, a crystal of zircon. Locked inside these tiny grains is a vital clue. Chemical analysis of zircon crystals reveals whether they formed in the presence of water. Over 7 years, Moyges finds and dates nearly 100,000 crystals of zircon. One stands alone.
The oldest one that we've found so far is 4.38 billion years old. Now, I'd like that to sink in.
When this crystal was made, the Earth was just 180 million years old. If this line represents the age of the Earth, then the dinosaurs died out here. Rewind about 4 billion years to the end of the Dark Period. The zircon crystal was formed here.
We're talking about time spans that are beyond comprehension. So for instance, in this rock here, there are zircon crystals that are 1/3 of the age of the universe. So these things have been around for almost as long as the Earth has been a planet. Talk about time capsules.
Analysis shows this 4.4 billion year old zircon crystal forms in liquid water. Rather than a dry planet, the crystal reveals that early Earth already has water on its surface.
When we made the discovery, that was very, very exciting because it wasn't fulfilling a hunch, it was true discovery. We didn't know what we would find.
For years, scientists thought that planet Earth forms dry. Moyges' discovery means that theory is wrong. Professor Mike Drake is searching for a new theory about how the early Earth forms wet.
Now, zircons tell you for sure when liquid water had to be present, and that's about 4.4 billion years ago. And all of a sudden, we don't know where it came from. We've suddenly got a major problem. We have to seriously consider the possibility that water was present in the building blocks of the planet as it formed.
But how could water exist in the building blocks if the blocks were boiling hot? The answer requires another step back in time.
I finally went back to what the system looked like 4.5 billion years ago before there were any planets, and realized we had these fine grains of dust embedded in a sea of hydrogen and helium and oxygen, and some of the hydrogen and oxygen reacted to make water. So we basically had dust surrounded by water.
Over millions of years, the dust and gas condenses to form the planets in the solar system. Far from the Sun, Jupiter and Saturn form with icy cores. But ice isn't the only way planets can lock in water. Further in, where it's too hot for ice, water can be locked into rocks, as this mineral demonstrates.
If you look at it, it looks really dry. If you touch it with your fingers, it's really dry.
But heat unlocks its secret.
And now you can start to see it's really boiling up into little balls of water. There's a huge amount of water coming off of this mineral. So a perfectly dry-looking mineral can contain a huge amount of water.
When the solar system first forms, the massive cloud of gas and dust traps the heat of the young sun. Where Earth forms, it's well over 1,000 degrees Fahrenheit. Too hot for such water-bearing rocks to form and build the planet. Yet soon after its creation, Earth manages to get water. Drake asks himself a new question. What if the early Earth traps water another way? A way nobody ever imagined.
One day I was drinking a nice cold drink, and I looked at the glass, and it had condensation on the outside of it, like this one does. You can see the water vapor on the inside if I run my finger around it. And I wondered if the same kind of process could have occurred in the disk around the sun 4.5 billion years ago. Could water have condensed out onto grains, much like it has onto this cold glass?
It's completely different to water-bearing rocks. If water vapor sticks to the grains of dust that build the planet, they could be the source of the oceans. An entirely new way for planets to form with water. He tests the theory with one of the main ingredients of planet Earth.
The green mineral in this rock is olivine, and olivine is the most abundant mineral that you find in the rocky planets. It's also the mineral that was abundant in the disk around the young sun 4.5 billion years ago.
He wonders if all the grains of olivine that form the planet have water stuck to them. He uses a computer to calculate the interaction between olivine grains and water vapor in the very early solar system. Water molecules stick to the olivine crystals.
So 30 grams of olivine allows me to absorb about 0.3 milliliters of water.
But can you capture enough water to fill the oceans? Drake has to scale up his calculations. How much water could stick to an Earth-sized pile of olivine grains?
Frankly, when we started these calculations, we didn't have a clue about how much water we could absorb. And we were actually astonished when we discovered we could get 10 times the amount of water that's currently in the Earth's oceans.
Professor Drake believes as the early Earth forms, it already has billions and billions of gallons of water. Water that sticks to the trillions of grains of dust that build the planet.
It's really exciting to have come up with a new solution to one of the most fascinating and important questions that humans face, and that is, why do we have any water? Because without water, we cannot exist.
But Drake's theory is new, and not everybody's buying it. It has a flaw even he can't explain. The type of water. Our water has a signature. The ratio of heavy to light hydrogen in the Earth's water tells you where it comes from. The source of Earth's water should have a matching signature. But the water that condenses directly from the disk of gas and dust around our young sun is very different. It would look and taste the same as Earth's water, but it would have 6 times less heavy hydrogen.
Now, I don't mean to pretend that we've got the entire answer yet, and until we can show we can get the right ratio of heavy to light hydrogen, we cannot be certain that this process is responsible for the Earth's oceans.
If Earth's water doesn't come from the building blocks that form the planet, and it doesn't come from comets, where does it come from? Professor Alessandro Morbidelli has developed his own theory.
All of a sudden, everything fits together. And you feel you understand the piece of your past that nobody was there to observe.
Are the origins of Earth's water finally about to be revealed? The origin of Earth's water is one of the biggest mysteries in science today. Scientists are looking for a match. There must be somewhere in space that has the same kind of water as Earth. The answer may be locked inside this lump of rock and metal. Few people know more about these meteorites than Gary Huss.
Well, I grew up in the basement of a meteorite museum my grandfather had in Arizona. And so I'd go up and look around at the meteorites, and by the time I was 2, I knew all of their names. Once you get bit by a bug like that, you can't get rid of it.
While comets are made of ice and dust and come from the cold fringes of the solar system, a meteorite comes from somewhere else. Orbiting the sun between Mars and Jupiter are millions of lumps of rock and metal called asteroids. Some, 200 miles across, weighing millions of tons. Leftovers from the formation of the planets. Sometimes asteroids collide, and fragments fall to Earth as meteorites. But what can they tell us about the origin of Earth's water?
The initial idea 100 years ago was that you had a major planet and it broke up and everything was dry and hot.
Looking at meteorites under a microscope reveals a different picture.
As we learn more about meteorites, it turns out that some of them are actually quite wet, a few percent water.
This is a slice of a meteorite, known as a carbonaceous chondrite. The bulk of it, the black stuff, is a mineral with water locked inside. This fragment of rock was once part of an asteroid that formed 200 million miles away. It reveals that at this distance from the sun, asteroids formed with water locked inside.
There's water in the asteroid belt, and it's apparently always been there. We just didn't know how to recognize it.
Is there any water in the asteroid belt identical to water on Earth? To find out, Professor Huss measures the ratio of heavy to light hydrogen in the water-bearing meteorites. He can do this with an ion microprobe.
We were actually quite fortunate to get one of the very first of this newest generation of ion microprobe.
The machine fires a beam of charged particles at the meteorite. This expels all the hydrogen atoms in the water. The heavy hydrogen and normal hydrogen are then separated so he can measure the ratio between them. What Dr. Huss finds looks like a crucial piece of the puzzle. The ratio of heavy to light hydrogen in the water in asteroids varies. But some have exactly the same ratio as the water on Earth. It looks like scientists have finally found where Earth's water comes from.
So then the question is, how do the two things from different parts of the solar system end up with the same kind of water?
Chemistry can't solve the conundrum. But mathematician Alessandro Morbidelli has a radical theory that could explain how water from the asteroid belt ended up on Earth.
The idea was driven really by measurements, by the fact that the water on Earth is so similar to the water that we get from meteorites that come from the asteroid belt.
Morbidelli took a revolutionary look at an old subject, how the planets in our solar system were built. Before, scientists looked at the formation of the 4 planets closest to the sun. They studied how matter near the sun condensed into bigger bodies, eventually forming the planets Mercury, Mars, Venus, and Earth. Morbidelli has done something radically different. He's the first scientist to look at the formation of all 8 planets in the solar system as a whole. From Mercury, closest to the sun, to Neptune, 80 times farther out.
The solar system is entirely interconnected, and we cannot study the formation of a portion of the solar system neglecting the other regions of the same system.
You can't study the planets in isolation because they're all linked by one force.
The only force that matters is actually gravity. So these things are relatively simple. We don't need to invoke strange physics or strange forces or dark matter.
As the planets grow, they interact because of gravity. Morbidelli recreates this interaction with a computer model, giving him a ringside seat at the birth of the solar system. About 1 million years after the birth of the Sun, the disk of gas and dust in the inner solar system condenses to form about 50 mini-planets. During the next stage, these mini-planets collide and form bigger planets. This demonstration shows what happens. The oranges represent mini-planets near the Sun. It's too hot for them to form with water trapped inside. As you move out, it gets colder. 230 million miles from the Sun, it's cool enough for mini-planets to form with water-bearing rocks. Green vegetables represent mini-planets with water.
The Earth eventually will have to form in this region, so in a region which is very hot, where nominally there should be no water.
If you look at the mini-planets close to the Sun, Earth forms from local material.
The mini-planets orbit around the Sun on trajectories which are almost parallel, like this.
Mini-planets collide to form the Earth. It forms from dry material.
But in this case, the Earth, because it formed from mini-planets which were dry, will also be very dry. Luckily for us, this is not what happened, so we need to revise our model.
Because Morbidelli looks at the solar system as a the whole scenario changes. Enter a new player, Jupiter. Jupiter is the biggest planet in the solar system and one of the first to reach full size. It's 300 times more massive than Earth. And in the early days of the solar system, it's starting to throw its weight around. Represented by this silver ball, Jupiter's massive gravity disrupts the orbits of the mini-planets.
Now, the mini-planets, in particular those farther out, have a more irregular motion, and in this way, the mini-planets can mix with each other.
Earth now forms wet. Look at the formation of all 8 planets at once, and Earth forms from a mix of mini-planets, some dry, some wet. This model explains how Earth came to have similar water to that found in the asteroid belt.
All of a sudden, everything fits together, and you feel you understand a piece of your past that nobody was there to observe. These moments are fantastic. There are just a few moments like that in a career of a scientist, but even if it happens once every few years, those moments are so exciting that they are worth years of work.
Morbidelli's idea is now the leading theory of how Earth got its water. But it's not the whole story.
For the moment, it is the best answer that we have, but as we say, the devil is in the details. There are certainly some details we don't understand, so we need to keep working until we understand all of them.
The question is, what happens to the water on Earth during the continuing collisions with mini-planets the size of the Moon and Mars?
The energy of this collision is so high that it's capable of melting the entire Earth. In addition, it actually vaporizes some fraction of the Earth's rock.
If these collisions vaporize rock, how can the water survive? The origin of Earth's water remains unclear. Scientists have theories that can get the water to Earth, but can they keep it here? The final stage of Earth's formation is a series of cataclysmic collisions. Can water survive the process? The answer is in the night sky. Robin Canup has been working on the formation of the Moon for 13 years.
I think people are particularly fascinated by our moon because it's been our companion throughout all of human history and throughout all of the Earth's history. Every human that has lived has gazed upon the same moon.
The moon was formed by a collision between the early Earth and a mini-planet.
The leading idea for how the moon formed is known as the giant impact theory. Just as the Earth was finishing its formation, the Earth experienced a collision with another planet-sized object, something that was smaller than the Earth, but still comparable to the current planet Mars in its size. So this was an enormous collision.
The last of several giant collisions between mini-planets that form the Earth. Why does this collision result in a dry moon and not a bigger Earth? Robin has developed a computer model to find out. The key turns out to be the angle of impact.
When this collision first comes in, it's at an oblique angle. The impacting planet is sheared apart into this long arm of debris that then wraps around the Earth to form a disk.
In no more than the span of a human lifetime, the disk of debris condenses and forms the moon. So why isn't the moon wet?
If you distribute that rock out into a disk around the Earth so that the disk is very spread out and there's a lot of surface area over which that rock can lose its water, then the water will tend to evaporate and be lost.
The model explains why the moon is dry, but it doesn't explain what happens to the water on Earth.
The moon-forming impact is an event of such a scale that it's almost difficult to comprehend. If you've ever visited a volcano and seen the molten lava coming out of the Earth, that's what we mean by molten rock. That would have been the coolest material on the Earth after this impact. If you continue to heat that material even more, it will eventually actually vaporize. The moon-forming impact was energetic enough to do both.
These cataclysmic impacts should have driven off any water on Earth. The impact occurred about 4.5 billion years ago. And as this is the last cataclysmic collision that planet Earth suffers, the date is vital. Professor Moiges' zircons reveals Earth has water 4.4 billion years ago, very soon after the collision that formed the moon. If the collision had blasted Earth's water into space, where did the water in the zircons come from?
Since water was present here in liquid form and abundantly very early on and soon after the moon-forming event, it means that either the water was delivered very rapidly right after the moon formed, which I think is highly unlikely, or water was already present on or within the Earth before the giant impact that resulted in the formation of the moon.
So the Earth's water survives this last cataclysmic process of planet formation. But how? Professor Drake thinks the water has been here from the start. He has a theory about how it survives.
So the collision of a Mars-sized object with the Earth is an incredibly violent event. It'll melt the Earth. Now the obvious question is, if the Earth went through such a violent event, how did it manage to keep its water? Most people think that if you heat something up, you boil all the water off, but that's not actually true. Any water that was in the Earth will be dissolved into that molten rock. That molten rock or magma is literally a sponge for water. You can dissolve vast amounts of water in liquid rock.
The early Earth is a giant fireball of molten rock. Dissolved inside are billions of gallons of water. But how does this rock become our blue planet?
This red-hot molten Earth is going to have lots of water in it, and that water's got to go somewhere when the planet cools down.
The rocks in this Arizona desert reveal what happens as the cooling rocks solidify.
A rock that crystallizes deep inside the planet will have the water kept in the minerals that crystallize. Here we have some micas. This happens to be a granite. And that water will be kept in the planet for 4.5 billion years.
Rocks that solidify deep in molten lava can hold water. But lava near the surface forms a different type of rock.
Any rock close to the surface, this one, for example, right here, you can see the holes in it, is going to lose its water. It's going to make little bubbles, which is what these holes are. Now imagine that there was rock like this all over the planet crystallizing. Water gets out into the atmosphere. Just look at the mountain range behind me and imagine the amount of hot, steamy water that could be coming out of these rocks as they crystallized.
All over the planet, water vapor escapes from the cooling rock. Earth's atmosphere is dense with steam. 100 million years after the impact that formed the moon, Earth has cooled enough to form a crust.
And you'll have boiling hot rain coming down onto the surface of the planet, running down in rivers, and eventually making the oceans.
But the story is still missing a chapter. Many scientists believe Earth has more than one source of water. Where did all of Earth's water come from? According to the leading theory, water arrived when mini-planets from farther out in the solar system collided with the early Earth. But scientists suspect this isn't the whole story.
I personally think there's more than one way to get the water to the Earth.
Like comets. Analysis of comets shows they couldn't be the source of all our water.
We can be pretty sure that comets must have brought in some of the water, because we know comets must have hit the Earth. But the question is, how much? What is the fraction that they contributed?
The solar system may have furnished another source of water.
We've been hit by comets and asteroids, and some of the water may have come from there. But for me, it's a no-brainer. At least some, if not most, of Earth's water had to come from absorption of water under grains before the planet ever formed.
But did these different sources bring enough water to Earth to support life? It's now impossible to work out how much of Earth's water comes from which source, because the water has been mixing for over 4 billion years. And over all that time, Earth's water has not only mixed, but changed.
The Earth's oceans basically have gone through a lot of processes since the Earth formed. There's rain and snow, and all of these things have caused the composition of the water to change a little bit.
By how much the water has changed, nobody knows. But there's a place where we might find out. A volcanic island chain in the middle of the Pacific. On the Big Island, Hawaii, Dr. Gary Huss is searching for the oldest water on Earth.
The Hawaiian Islands volcano is basically what's known as a hot spot.
A place where lava steadily oozes from the Earth.
The rocks that we're standing on in the Hawaiian Islands come from the very deepest part of the mantle of the Earth, thousands of miles below the surface. And it provides us a sample of material we could never get any other way.
When he looks at water locked in rocks drilled on Hawaii, Huss is actually looking at water from the middle of the Earth. Water unchanged since day one.
If you want to look at what the composition of the water on Earth is at the time that the Earth formed, this is about the only place you can look.
Can Huss find evidence that there's primordial water deep inside the planet?
Oh, it's one of these guys? Oh, that's neat.
His approach is unprecedented, and early results suggest he might be onto something.
Well, this is good. This is a great sample for your purpose.
When we first found the hints, we definitely got excited about it. It does look like the water from deep in the Earth is different from the oceans, and it's different significantly.
So different, it could be primordial water, untouched since the birth of the planet. This research could ultimately deliver extraordinary answers to the question of the origin of Earth's water. And Hawaii isn't the only test site. The team is also sampling water from another hotspot, Iceland.
If we can nail this down for, say, the Hawaiian volcano, and then we can go to the Iceland hotspot and we get a different answer. Not only now do we have differences between the deep water and the surface water, we've got differences between a volcano on this side of the Earth and a volcano on that side of the Earth. There may be evidence for more than one source at this point.
One day, deep inside the planet, they may find reservoirs of primordial water different from each other. Such a discovery would mean one thing: our water must have different origins. The implications are profound. For years, astronomers have been working toward one goal: scouring the skies in search of another planet like Earth. A rocky planet, just the right size and just the right temperature for liquid water and life.
We know now of 250 other systems that have planets in them, and we haven't found an Earth yet.
Billions of systems are yet to be explored, so the numbers are on your side if you're looking for another Earth.
We have 100 billion stars in our galaxy. Of them, we think about 10%, so 1 in 10 is a sun-like star. And we think that maybe 1 in 10 of those stars has planets. So that's about 1 billion stars in our own galaxy we think would have an Earth-like planet in it. Now, whether it has water on it is a different story.
Do any Earth-like planets out there have water? Could any support life? Today's telescopes can't answer that question, but computer models can. Dr. Sean Raymond has devised one.
We take our cues from observers. So with telescopes, people go out and find giant planets orbiting other stars. Then we take the orbits of those giant planets and try to figure out, in that system, could you still form a planet like Earth?
Raymond's computer model shows as planetary systems form around stars, some Earth-like planets end up with water.
We're modeling the formation of a planetary system here. All this red stuff is dry, the blue stuff is wet.
He starts with lots of mini-planets. Far from their sun, the blue ones have water. Closer in, where it's hotter, the red ones form dry. As the planets form, they start to cool. Like Earth, any planet warm enough to have water must orbit in the dry zone.
This guy right here is going to end up being a pretty good Earth analog.
The model shows how wet mini-planets from further out are pulled in to collide with a mini-planet in the dry zone, like Earth.
And there you just saw it turn from red to yellow to green. That's water delivery happening right there. And by the end of this particular simulation, it's very wet.
The result is a planet in just the right place for water, another Earth. Using the model, Raymond can calculate what's needed to form other Earths and how many there might be.
And we say, what if things were a little bit different, like we think they are around this other star? How would that affect the formation of planets like Earth, and how would it affect water delivery to those planets?
If Earth's water was delivered in more than one way, via comets, and with water as one of its initial ingredients, suddenly, the chances of finding an Earth-like planet with liquid water have just shot up. So too have the chances of finding alien life.
This is a big deal because are we alone in the universe, right? No one knows for sure. Everyone's excited about life on other planets. And what we're doing is one step towards trying to find life on those planets. It's really cool. I mean, it's very exciting.
And because scientists now think planets can get water more than one way, they're more confident than ever about the answer.
When people ask me if there's life out there, I say yes. And is there life like we know it, with a rocky planet where water has been brought to it? I think the answer again would be yes.
So by finding out how Earth got its water, we can find out how likely it is that out there somewhere, maybe millions of light years away, there are other alien forms of life. This is nature at her worst. Shredding buildings, drowning cities, killing thousands.
The hurricane is the most deadly and powerful system or phenomenon you're going to find on this planet.
They're the largest storms on Earth. How they gain such power is a puzzle with missing pieces. Scientists follow the life cycle of these killer storms, from birth to death, to solve the mystery. They are one step closer to parting the clouds, to reveal the anatomy of a hurricane. Hurricanes, nature's fury. A single strike can cost billions. Every year, hurricanes claim lives around the world, and they're becoming more powerful.
You have this whole devil's brew of things going on in a hurricane. Incredibly high wind, waves crashing on shore, intense thunderstorms. It's just an incredibly scary blend of things happening all at once.
Scientists struggle to predict where a hurricane will strike and how powerful it will become. Only by studying it from cradle to grave can scientists learn how it functions and perhaps forecast where and when it will hit. This is the story of science against nature at its most furious. Lives depend on the outcome. Over 80 hurricanes form each year around the world. Of those that form in the Atlantic, roughly 1/3 will strike America. The names are familiar: Andrew, Wilma, and Katrina. The future will bring new tragedies. And the race is on to understand how hurricanes work. Chris Lancy from the National Hurricane Center is trying to crack the hurricane code.
One of the primary goals of the Hurricane Research Division right now is to better understand the life cycle of hurricanes at their infancy, at their beginnings, the genesis, and to maturity, and then to the decay.
Ignition. The search for answers starts thousands of miles above the Earth. Satellites allow researchers to spy on a weather system born far out of sight of land. Images taken 22,000 miles above Earth reveal the genesis of the storm. 85% of major Atlantic hurricanes actually start in one of the hottest, driest places on Earth: Africa. In summer, the vast Sahara heats the air above it. As the air warms, it rises, climbing over 2 miles. The warm air pushes the existing weather patterns higher, forming an atmospheric disturbance. Scientists call this the African Easterly Wave. It travels west across Africa at about 500 miles a day. Converging winds on the east side of the wave trigger the development of thunderstorms, the seeds of our hurricane. Over the warm waters of the Atlantic, the thunder cells grow and merge. Atmospheric pressure within the weather system drops. Winds rush in to fill the gap and grow in strength. When they reach 23 miles per hour, meteorologists call it a tropical depression. Computers at the National Hurricane Center track every growing storm. Getting information as early as possible is crucial.
If we can't forecast, the genesis or beginning, we're going to be behind the curve in forecasting the rest of the formation of the storm itself.
Satellite data is vital, but it's not enough. They need to see inside the storm. That's the job of Jim McFadden, hurricane hunter.
You have to know what's going on in the storm full time. And the only way to get the information like the highest wind speeds, the lowest pressure in the center of the storm, is to actually put a plane into it.
The Hurricane Hunter's workhorse is the Lockheed WP-3D Orion turboprop aircraft, packed with scientific instruments and radars. They load data-collecting probes and fly out to meet fledgling hurricanes 5,000 feet above the waters of the Atlantic Ocean. The thunderstorms within the depression group together. Atmospheric pressure keeps dropping, causing wind speeds to increase. When they hit 39 miles per hour, the depression gets reclassified. It's now a tropical storm. The storm pulls in air over such vast distances, the air streams actually curve. Greg Holland explains how the thunderclouds begin to spin.
It steals some of the rotation from the Earth system to actually give it that turning. It's an effect we call a Coriolis force.
The direction of the storm's spin depends on whether it forms in the top half of the Earth or the bottom. In the northern hemisphere, the Coriolis effect pulls winds to the right and makes the storm spin counterclockwise. In the southern hemisphere, the wind is pulled to the left, which makes the storm rotate clockwise.
If there was no Coriolis, the hurricanes probably wouldn't spin up because the low pressures would be filled and that would be the end of the storm.
Rotation alone can't turn a tropical storm into a hurricane. Up to 28 tropical storms form each year in the Atlantic. On average, only 6 become hurricanes.
You have to have a few kind of key ingredients. You could almost say it's like a hurricane recipe for things to begin. One of which is you need a bit of spin to get things going. Another key ingredient is you need thunderstorm activity. Hurricanes are fueled by the thunderstorms. And the third key ingredient is you need a warm ocean. You need waters at least 80 degrees Fahrenheit for enough energy to be available for those thunderstorms.
The warm waters of the Atlantic Ocean act as fuel for the growing storm.
It's sort of like you go down to the tank and fill up your car. You put a certain amount of energy, if you like, into the car, and then you can drive at a certain distance.
As the surface water temperature of the tropical Atlantic rises, trillions of energy-bearing water vapor molecules evaporate into the atmosphere. They rise higher, they cool, and condense into clouds. This process releases heat, which warms the air around it, pushing the clouds even higher. Now the storm towers 10 miles high. The air within is no longer warmer than the surrounding atmosphere, so it stops rising. The system flattens out to form an anvil cloud. There's still one thing that could stop the storm from becoming a hurricane. High-speed, high-altitude winds. These can shear off the top of the storm, destroying its structure and the flow of energy within it.
You need what's called a minimum of wind shear. And wind shear is just the changing winds with height, the difference between just above the ocean and about 8 miles up. If that wind difference is about 20 miles per hour or greater, hurricanes don't form.
In the growing tropical storm, the wind shear is low and it continues to gain strength. As the winds hit 74 miles per hour, it gets a new name. This is now a hurricane. It has the potential to become the most destructive weather system on the planet. The hurricane is 200 miles across and heading straight for land.
Whether you're flying into it by aircraft or watching from space from our satellites, then it's approaching its most beautiful stage. So people like seeing them to some degree, but we also realize the horrible problems that hurricanes can cause.
McFadden's Hurricane Hunter team have to fly into these killer storms. With data from the eye of a hurricane, scientists can estimate how powerful the storm might become. The center of the storm is still hundreds of miles away, when the hurricane hunters hit the first rain bands. These are fierce clusters of thunderstorms that spiral out from the center. They form as water vapor evaporating from the ocean rises into rain-bearing clouds.
We usually pick our way through the rain band so that we avoid most of the severe turbulence in a rain band, and then on towards the eye wall.
The eye wall is a dense wall of cloud around the hurricane's eye. It's where the weather is most extreme. Here, winds can reach 200 miles per hour. The rain is torrential.
It's where a lot of the upward transport of moisture, the conversion into clouds, and the heating occurs to get the cyclone going. So this, if you like, is the pistons of the heat engine of the hurricane.
The hurricane hunters make it through the eye wall. Inside, a circle of calm weather up to 40 miles across. The eye is the heart of the storm, the pivot the hurricane rotates around. At the center of the eye, the air is relatively still. No rain, blue skies.
When we fly into hurricanes, you don't see much, and you're going through the eye wall. It gets very dark, and then all of a sudden, the plane goes smooth, and we're in the eye, the calm part. And you're blinded for a second because the sunlight is so intense, and your eyes finally get used to what's going on. You look around, and you're in this, it kind of looks like a gigantic bowl. It's like a 40-mile wide football stadium, just what a hurricane looks like.
McFadden's mission is to drop a probe into the heart of the storm.
This is one of our GPS drop-ons, and it's proved to be probably one of the most important tools for collecting data in hurricanes that we've had over the last 10 years.
The probe parachutes down through the eye and measures the hurricane's temperature and humidity twice a second. Built-in GPS gives data on wind speeds and direction. But the most important reading is atmospheric pressure. As the hurricane grows, the pressure at its center drops. The area of low pressure sucks in more warm, moist air. If the hurricane hunters can get a pressure reading from the eye, meteorologists can estimate how powerful the storm may become and how long it may last. They also monitor the size and shape of the eye. As the storm gathers strength, the eye can contract, making the winds even stronger. In 2005, Hurricane Wilma did just that.
What this is a loop of the satellite imagery. And so this gives you a sense of the evolution of the whole life cycle of Hurricane Wilma. And you'll see the development of the eye, very tiny eye. When you get a pinhole eye, a very tiny eye, that's often indicative of a very small inner core. And in general, as the eye and eye wall gets smaller, you tend to have faster winds, stronger winds. It's analogous to an ice skater. As she brings her arms in and she's rotating, she spins faster.
Scientists classify the hurricane's strength according to its highest sustained wind speed, taken over a 1-minute period at 33 feet. Category 1, wind speed 74 to 95 miles per hour. Category 2, wind speed 96 to 110 miles per hour. Structural damage to roofs. Category 3, up to 130 miles per hour. Many buildings irreparable. Category 4, winds up to 155 miles per hour. It smashes solid walls. Category 5, the deadliest. Large-scale destruction and widespread flooding. Little can survive a Category 5 hurricane. In the Atlantic, the approaching hurricane is still a Category 1. Ahead lie 2,000 miles of warm water, fuel for a thirsty storm. The battle now is to predict how powerful it will become and where it will strike. A killer hurricane stalks the Atlantic. 8 days ago, it was just a cluster of thunderclouds off Africa. Now, it's a Category 2, over 200 miles across, winds near 100 miles per hour, and rising. In less than 48 hours, it will hit America. But where?
Nowhere is safe on the Gulf Coast or the East Coast of the United States. And the more we can understand of the dynamics of these storms, the more we can understand what exacerbates the impacts, the better it is for everybody.
It's vital for meteorologists to understand why hurricanes take a particular path. If they can better predict where these killer storms will hit land, they can broadcast more accurate warnings and save lives.
Now, how a hurricane moves is due to a number of different factors, of which there are two main ones. The first is that it acts just like a cork in a stream. It is actually blown along by the large-scale atmospheric winds in which it's embedded. Then the other major component is that they actually use up a little bit of the Earth's rotational effect to allow themselves to push themselves along.
To predict where the hurricane will strike, meteorologists need information about the weather systems that surround it. The trade winds, a prevailing pattern of winds found in the tropics near the Earth's equator, push the hurricane west at speeds of up to 20 miles per hour. But before the storm makes landfall, it must negotiate a region of high pressure off America, known as the Bermuda High. This high-pressure dome moves across the Atlantic and creates winds that spin clockwise. Depending on its size and position, it can steer a hurricane harmlessly into the Atlantic or straight into land.
It's the changes in the wind flow that are important. Whilstsoever the wind is in one direction, it's great for forecasting because it makes it really easy. It's when they're at that change state that it becomes very, very difficult.
Meteorologists have recorded the paths, frequency, and intensity of Atlantic hurricanes. Where and how a hurricane strikes can appear random. Scientists use computer models to try to establish patterns to better predict where and how powerfully it will hit land. Joe Cione works to improve the data that inputs into these models.
What models are doing are trying to, as closely as they can, simulate exactly what Mother Nature is doing. And once we get to the point where we say, you know, we have done that, we have improved the model's representation of nature, what will result is improved forecasts going forward.
Over the last 20 years, computer models have made huge advances. Faster, more powerful processors, better weather data, and greater knowledge of hurricane anatomy allow meteorologists to make better forecasts. Robert Rogers and his team at the Hurricane Research Division play a key part in piecing together this puzzle.
The track forecasts have improved significantly, but our intensity forecasts have essentially remained constant. They have not improved or improved very little over that time. So we have our work cut out for us, and that's really what we're focusing on now.
Scientists now have a much clearer idea of where a hurricane will strike. Estimating how powerful it will become is tougher. The hurricane tracks 500 miles south of Bermuda. It's now just 36 hours from landfall. It's already a powerful storm. If it hits an ocean current or eddy where the water is even warmer, it could rapidly intensify. The warmer the water, the more powerful the storm.
And it's sort of like you put a bit of turbocharge into your car. Suddenly it's got more fuel, suddenly it can actually start accelerating its intensity, and away it goes.
It's what meteorologists fear most, a storm that gets a kick of energy.
From a forecasting standpoint, that's kind of the nightmare scenario. So whereas, people went to bed one night expecting maybe a Cat 1 to make landfall, they might wake up the next morning and looking at a Category 3 or Category 4.
Scientists don't know why some hurricanes rev up and others don't. The answer may lie in a part of the hurricane called the boundary layer. It's the region at sea level where the hurricane draws its energy. where sea and air interact.
So if we want to really get a good handle on intensity change, we have to understand how the energy is transferred out of the ocean.
Sion is part of a team trying to unravel what happens at the boundary layer. To bring back the data, scientists must skim over waves up to 3 stories high and fly straight into one of the most dangerous places on Earth. The hurricane is 36 hours from hitting America. Winds near its eye blow 115 miles per hour. It's 300 miles wide and still growing. Question is, will it get a jolt of power? Some scientists believe the answer lies in the boundary layer. It's here the storm draws heat from the sea as fuel. Scientists need to refine their understanding of the exchange of energy that happens here and how wind speed, friction, humidity, and air and sea temperature affect how the hurricane intensifies. Until recently, scientists lacked reliable data from the boundary layer. September 2003. As part of an experiment called Sea Blast, hurricane hunter planes flew straight into the deadly boundary zone of Hurricane Isabel.
Sea Blast itself was to look at the dynamics of the boundary layer in a hurricane. We were willing to fly down to 200 feet as long as we can maintain visual contact with the surface.
Below, a churning mass of 40-foot waves. Around them, wind eddies that could swat them out of the sky.
When you're flying that low, you can see every single wave. And some of these 30 or 40-foot waves look visually like they're about to touch the plane.
They flew so low, sea spray drenched the plane.
We noticed that the windshield was turning white while we were flying at 200 feet in a hurricane. We didn't realize, though, that all that salt was coating the engines.
One of the engines had a problem, and we had to secure it, turn it off.
They regained power just in time and limped back to base. Their data gave scientists fresh insight into how wind speed affects the amount of energy entering the storm. As a result, new data was fed into computer models. Data from the boundary layer will improve the accuracy of forecasts. But data from these missions isn't enough. And Operation Sea Blast proved flying through the boundary layer is too risky. How to get more data without risking lives? Don't send people, send a probe.
What you're looking at here is the Mark III aircraft. It's an Aerosonde Corporation aircraft. That we think that this is a very compact aircraft that can do a lot of things and measures what we needed to measure.
Sion's team loaded the Aerosonde with instruments to measure meteorological conditions within storms. It headed toward the hurricane's strongest winds, piloted via satellite.
Only 100 miles since our turn.
In 2005, they flew into Tropical Storm Ophelia.
We rode it up and down, and the aircraft survived that. And this is the first time we've really been able to look at data like this.
The Aerosonde can fly into the deadliest parts of the hurricane and stay there up to 12 hours.
The only thing I can compare it to is what I saw on TV with these Mission to Mars, where the group of scientists send something out and you see them cheering when it finally gets on the surface of Mars. You just feel just a great sense of accomplishment. And for me, it goes beyond that too, because I know what we're doing is really, we're trying to help people. We're trying to save lives.
Scientists hope that in the future, Aerosondes will regularly fly into the hurricane's boundary layer and send back constant data. This will improve their understanding of how storms intensify and help them spot the warning signs. The better the forecasts, the more lives saved. 24 hours from landfall, the hurricane has strengthened to Category 5, a 350-mile wide heat engine. It converts the warmth of the sea into winds over 155 miles per hour. Inside the storm, rising water vapor and churning seas mean the hurricane picks up 2 billion tons of seawater every 24 hours. The rains inside the storm are torrential. The path is set. Hurricane historian Jay Barnes knows what happens next.
Here we have a hurricane about to strike land. We know what is going to happen because we've seen it happen before. A powerful storm, very, very large in diameter, going to affect hundreds of miles of coastline.
A hurricane's biggest killer is water. Not rain, but a wall of water called a storm surge. 90% of all hurricane deaths are from drowning. Oceanographer Stephen Begg watches the Atlantic for the first signs of the surge.
Storm surge is not something that's been seen by very many people, and even fewer survivors, so that it's hard to describe to people.
Forecasters monitor the hurricane closely. From the wind, Ivar Van Heerden picks up clues about the size of the surge.
The stronger the winds, the more water you blow towards the shore, the more surge you're going to see.
As the first part of the eye wall hits the coast, winds accelerate. The surge reaches its peak.
The surge intensifies as the eye gets close because the strongest winds are around the eye. So you then, under the influence of the stronger winds blowing the water landwards, piling it up on top of what's already been piled there, and that's when you get the intensification.
The highest winds blow on the right side of the storm. If the right side strikes first, the surge will be worse. That's because the hurricane is not only spinning counterclockwise, but is being driven by winds across the sea. On one side, spin adds to forward motion. On the other, it subtracts. A storm spinning 90 miles per hour and moving forward at 10 will have winds of 100 on the right side and 80 on the left. The higher the winds, the higher the surge. August 2005. A Category 1 hurricane struck Florida, then transformed into a 400-mile-wide killer in the Gulf of Mexico. It was set to strike the Gulf Coast, right-hand side first. The hurricane's name, Katrina. Professor Van Heerden watches the path that Katrina is taking.
We started to suspect that Katrina potentially could hit New Orleans even before it made landfall in Florida. And the reason being the weather patterns were such. The Bermuda High had moved a little bit to the west, that the wind currents would be bringing anything that entered the Gulf of Mexico into Louisiana. The curvature was there. And of course that proved true.
At 6:10 a.m. on the 29th of August, Hurricane Katrina hit the coasts of Louisiana and Mississippi. In the midst of the carnage is storm photographer Mike Tice.
The storm surge was coming up to Highway 90, and by 8 o'clock, it was already coming to the front steps of the hotel. When the storm surge started to get around 12 to 15 feet, it made it into the first floor of the hotel, and a car comes floating through the hotel lobby. I saw it coming ahead of time in the parking lot. It perfectly came in, so it came directly through the front glass doors, crashed into them, And the horn started honking, the lights started flashing. It was echoing inside this lobby. Of course, all the power's out. It's pitch dark in there. And it is one of the most horrifying, scary things I've ever seen in my life. It was straight out of a scary movie, and I don't think I could ever have imagined I would ever witness something like that in my life.
The highest storm surge ever seen in America sweeps across the entire region.
This rise of sea level in some areas estimated over 27 feet. And if you can imagine the beachfront like we're standing here today, a 27-foot elevation of the surface of the ocean, with waves, battering waves on top of that, it's quite destructive. And that's what caused the tremendous destruction we saw along the Mississippi coast.
The surge built along the Mississippi Delta. In New Orleans, the levees burst. A city drowned.
We knew that we were going to be dealing with very high death rate. 10 years of research, looking at lots of other floods all over the world, just cannot prepare you to see miles after miles of subdivision and only the roofs are visible. And of course, on the roofs, people frantically waving for help.
Over 1,500 people died. A tragic testament to the power of storm surge. Now it's the turn of the hurricane's eye to hit land. The storm passes over its own havoc. For 1 hour, the rain stops. Clear skies and sunshine break through. What was destroyed in just hours will take years to rebuild. And still, we have seen only part of the hurricane's deadly arsenal. More damage is coming. The hurricane is only half over. Its other lethal weapon returns for a second attack. Wind. "10 days ago, this storm was a cluster of thunderclouds off Africa. Now it's a hurricane at the height of its destructive powers. The storm surge caused terrible devastation. Winds cause even more. As the eye passes over, the other side of its wall hits, and the winds switch direction. At first, this helps. Floodwaters are pushed back out to sea as quickly as they came.
As soon as the eye goes by, the winds start blowing from the opposite direction and starts blowing the water offshore, so that you get the very rapid set down.
As the deluge of water drains away, the hurricane begins to move further inland. Its strongest winds, over 155 miles per hour. The eye wall.
The winds are toppling power lines and knocking down trees, blowing the roofs off of homes and smashing windows. It really is a scene of chaos as the most powerful part of the storm strikes the coast. That's when you see the greatest intensity of impact.
Low pressure pulls air in toward the center of the storm as wind. The closer to the eye, the faster the winds. Some of the inrushing air gets pulled into strong updrafts, and centrifugal force generated by the hurricane's spin pushes some air away from the eye. Most rams into the eye wall, creating a spinning tube of wind and cloud. Bob Henson studies the architecture of this force.
So in a mature hurricane, you've got this complex dance, and it's a very symmetric and beautiful thing, actually.
This delicate balance of forces shapes the speed and direction of the hurricane's internal wind.
So what you really have in a hurricane is wind parcels rotating around the center of the hurricane, like the nickel is here, but spinning faster and faster as it nears the center and tries to rise up, and then finally does rise through the very center of the hurricane, as we're seeing right here. That's what actually happens in a hurricane.
A hurricane's strongest winds are just above the ocean and close to the eye wall. Away from the center, winds slowly weaken, Yet even 60 miles from the core, it gusts well over 100 miles per hour. The damage can be colossal. At the University of Florida, scientists are working with engineers to design hurricane-proof homes. The first challenge for Forest Masters is to test buildings under realistic hurricane conditions.
So we're trying to understand, how does the whole building perform, in concert to resist these extreme loads.
To test how a building will perform, Masters measures hurricanes at work. His team deploys hurricane-proof towers, loaded with equipment, to measure the winds 33 feet up.
It's incredibly dangerous deploying this kind of instrumentation in the path of a landfalling hurricane. We don't have a lot of time. We wait to the last possible minute to be certain that we know where the storm is going to go.
The data lets Masters map the wind itself. His results confirm the winds change radically once the storm moves off the ocean and hits land. Buildings and even the ground itself cause friction and reduce average wind speed. But as winds are forced over obstacles, gusts become more intense. These turbulent blasts of air can turn a home into matchsticks in minutes. Masters feeds data from the towers into a hurricane simulator. He aims to recreate a Category 3 storm to test how a window performs. This machine really blows. 8 5-foot-tall industrial fans, powered by 4 vast engines, produce the winds. A 5,000-gallon water tank cools this vast machine and provides the rain.
We're taking that turbulence data and we're trying to replicate that at sufficient scale to immerse a low-rise building. And that allows us to look at the performance of all the different parts of the building, such as the windows, doors, and roof cover systems.
The simulator mimics the gusts and driving rain of a typical hurricane. If the hurricane can get inside doors and windows, the difference in pressure can tear the house down. This window is being hit by Category 3 force winds. So far, it's impervious. Piece by piece, the team tests windows, tiles, studying the ways in which hurricanes expose flaws in design and assembly.
Ultimately, if we can make better buildings, stronger buildings, perhaps we can modify our evacuation policies so that people can stay in their homes longer, or in a higher and more intense events.
As the hurricane travels inland, the value of this type of research is obvious. Buildings with any weakness are ripped to shreds.
My house has just launched a whole bunch of missiles into the air, which is going to damage your house. Your house is going to launch a bunch more missiles into the air, which is going to damage the next house down. And suddenly we have this mass of flying debris that is doing an enormous amount of damage.
The storm moves 15 miles inland every hour. The further it moves away from the ocean, the weaker it gets. Winds drop by half every 7 hours. The hurricane is dying, but it's not dead yet. The hurricane hits land as a full-blown Category 5 storm, a blast of destructive energy. It creates vast floods and devastates coastal towns and cities. But as it leaves the ocean behind, it loses power. A hurricane needs fuel.
When a strong hurricane makes landfall, you see some changes to the characteristics. The structure starts breaking down.
Really, over just a few hours, the death warrant has been written.
The energy source was heat from the warm ocean. Dry land lacks the fuel to keep it going, and the storm's heat engine stalls. The hurricane releases more energy than it gains. Its internal structure the inflow and outflow of air disintegrates.
If you're going to write an autopsy of a hurricane that makes land, it probably would say death by lack of warm water, because once the hurricane has moved off the ocean, it's lost that source of heat that sustains it.
Near ground level, the inflowing and outflowing wind meets friction from land, trees, and buildings. The low-level winds die. With no energy coming in, the storm's air circulation falters.
In addition, the winds start to feel the trees and the houses, which impact a lot of friction, and it slowly but surely spins down.
It's like a car running full throttle on an ounce of gas. In one day, a Category 4 hurricane can shrink to a mere breeze. If the hurricane hits mountains, it will die even faster. But sometimes, the storm is thrown a lifeline.
Sometimes a hurricane may briefly re-intensify, and this is a process that's rare and not well understood, but if it passes over very moist land or a marshy area or so forth, it may get a little pulse of energy, and if other conditions are favorable, you might get a brief spin-up.
August 24th, 1992 at 5:30 a.m. Andrew slammed into Florida as a Category 5 storm. After landfall, its winds faded. It limped across Florida for 4 hours, passing over the Everglades. Warm, shallow water temporarily nourished the storm and allowed Andrew to make the deep waters in the Gulf of Mexico. Andrew revived and became a Category 4 storm. It pounded Louisiana. It took another 24 hours for Andrew to die, this time for good. The death of a hurricane marks the beginning of its autopsy by the scientists.
We do an evaluation of the storm itself, the whole life cycle from birth to maturity to decay, and try to summarize that as well as the impacts on people.
Scientists have improved their track prediction by 50% in the last 20 years. Huge advances are being made in forecasting just how strong a storm will become. But they may have to factor in a new twist. What will be the impact of rising global temperatures?
We've had a lot of Category 5s just within the last few years. So there's been a lot of discussion and a lot of questions about are we seeing an impact from global warming on this hurricane or that hurricane?
Climatologists combed through more than a century of records. They found that average ocean temperatures in the tropics have risen by 1 degree Fahrenheit. Hurricanes get their energy from warm water. Logic suggests stronger hurricanes. In 2008, the United States Climate Change Science Program announced their conclusion. It points to an increase in hurricane intensity or strength.
It is very likely that the oceans have warmed up due to climate change. It is very likely that we will see, and indeed are seeing now, increases in rainfall in hurricanes because of this, and increases in the maximum intensity.
For now, meteorologists concentrate on the present. Their work continues to reveal new aspects of the birth, life, and death of the deadliest weather system on planet Earth.
We've reached the point where our meteorologists are doing a super job of telling us where they are, where they're going, and what to expect. Well, one of the things that we can all expect is that they're going to keep coming.
Science has shown us the anatomy of a killer. We can't prevent them, but we can learn to predict them. With each new piece of the puzzle, science saves more lives. The power of a hurricane is awesome. They're striking earlier than ever before.
I realized that this was going to be a historic event.
They're getting stronger.
Is there anybody else in there with you? Do you need help? Is there anybody else down here?
And they're striking places they've never been.
If you're living north of Tornado Alley, sometime in the future, tornadoes will start showing up on your doorstep.
Tornadoes are changing. The events of one tragic day will tell us why. A terrifying glimpse of the future that holds the key to saving lives. February 5th, 2008. Super Tuesday. Out across the Central Plains, a storm is brewing. This will be no ordinary storm. As cold, dry weather streams in from the Rockies, unseasonal warm air forces its way north from the Gulf. Where they meet, history will be made. No one expects to see this kind of weather in winter. The first sign of trouble arrives late in the morning. Massive thunderstorms are forming in a line over Texas.
My initial thoughts were I need to get the word out. It's obvious that we are dealing with a major storm system that will produce widespread dangerous weather and that people are at risk.
And by mid-afternoon, the system is beginning to develop the most powerful storms of all. Supercells. One hour later, the situation on the ground goes critical. The start of a trail of death and destruction that sees 87 killer tornadoes drop from the skies over Mississippi, Alabama, Arkansas, Kentucky, and Tennessee, wreaking more than $500 million of damage. "57 people will perish. One of the worst tornado outbreaks ever recorded. But the implications are far worse. Scientists looking at Super Tuesday see a dark future. Stronger, more destructive tornadoes striking outside the traditional tornado season. Striking in places they have rarely been seen before. Tornadoes are changing. So what exactly is happening? The answers lie in the rubble of Super Tuesday. Solving the mystery of this devastating outbreak is a matter of life and death. The investigators start with the biggest mystery of all. How does a tornado form? From here, they can work backwards and figure out what was different about the storms that gave birth to the tornadoes of Super Tuesday. What they know for sure is that tornadoes form in storms like no others. Hurricanes take days to develop, cover thousands of square miles, and follow a discernible path. They begin life in Tornado Alley, stretching from Texas through Oklahoma, right up to Iowa and Nebraska. vast and flat, and caught in an atmospheric crossfire between north and south. The weather here has all the right ingredients for twisters, and spring is traditionally tornado season. As winter turns to spring, polar air from the Rockies spills across the plains. It sets off on a collision course with warm, moist air heading north from the Gulf of Mexico. The stage is set. Warm air is light and wants to rise. Cool air is heavy and wants to sink. When the two air masses collide, they begin to spin. Tornado expert Robin Tanamachi has a simple way to demonstrate what happens next.
What we have right now is a very unstable arrangement. You can see we've got this very dense, heavy water up in the upper chamber, and the lower chamber is filled with air, which is much less dense than the water. And the air wants to go up into the upper chamber, the water wants to come down.
Scale this instability up a few thousand times, and you get vast thunderclouds called supercells, the birthplace of tornadoes. Compared to regular thunderstorms, they can span 20 miles across and tower twice the height of Mount Everest. Supercells are the most ferocious of all thunderstorms. But the energy in the storm needs an outlet. The cold air wants to sink, and the warm air wants to rise. In order to restore the balance and release the energy, another ingredient needs to be introduced.
You can see some of the air bubbles are kind of traveling up into the upper chamber, but this is a pretty inefficient way to restore the balance to this unbalanced system. And so what I'm going to do is impart a little bit of vorticity to the system by sloshing it around a bit so that now it spins. And now we have a vortex that's formed in the middle, so that now the air is flowing upwards through the center of that vortex into the upper chamber, and the water is flowing downwards into the lower chamber, so that this is a much more efficient way for the system to go back into balance.
The imbalance allows the warm and cold air to mix by spinning them together. It's the fastest way for the heavy air to sink down. This spinning is known as wind shear. This is the second vital ingredient for tornadoes.
So relatively weak winds at the surface, topped by stronger winds aloft, create this roll, and that is shear.
So they know how supercells are created. But why a supercell creates a twister is the last great weather mystery. It seems clues may lie in the spinning motion itself.
Many researchers who've studied them have sometimes called them accidents of nature because it seems so elusive to figure out what actually went together to cause the tornado at the ground. We know how to get a lot of spin in a thunderstorm, but there are definitely some more complex things going on near the ground. We can have spin taking place on small enough scales that we really aren't able to measure it.
Only one supercell in 4 gives birth to a tornado. So what makes that one so special?
We do not know yet what the mysterious missing ingredient is. We think we know what it takes to get a tornado, but there's something mysterious that we still don't understand that determines, sometimes a tornado will touch the ground, sometimes it won't.
But when it does, the results can be devastating. Once the funnel touches down, it starts feeding on an inflow of warm, moist air at ground level. This warm air is called updraft. Low pressure inside the vortex creates a vacuum, and the warm, high-pressure air around it rushes in. Once inside the funnel, the warm air shoots upward, trying to restore the balance, all the time sucking in more and more warm air from the ground. The warm air is the fuel that gives it the energy to move forward. Its funnel sucks up debris as it tracks along the ground. You not only see it coming, you hear it.
Don't go! Jesus Christ!
There have been descriptions of tornadoes that vary from a roar like a freight train, depending on how fast the tornado is moving. If they're inside of a house, they may report that it makes a very high whistling sound, say if it's coming through cracks in windows or something like that.
Yes, a large destructive tornado. There's a large tornado moving through the south side of Atkins.
On Super Tuesday, one of the worst tornadoes ever seen in Arkansas rips through the state, traveling a record 122 miles. Across 7 counties, it leaves 13 people dead. 100 homes in the little town of Atkins are torn apart. But what makes this tornado so unique is that it happens at the wrong time of year. Powerful tornadoes like this very rarely strike in winter, yet Super Tuesday sees 87 of them. Investigators now turn their attention from the tornadoes to the storms that made them. The answers they are about to uncover will bring them one step closer to understanding why tornadoes are going to get worse. On the 5th of February, 2008, a devastating tornado outbreak claims 57 lives and leaves experts baffled. 87 powerful tornadoes striking in winter is rare.
Once I sat back and realized it was only the 5th of February, then I realized that this was going to be a historic event.
Freak weather? Or is a pattern emerging? To find out, scientists rework the events leading up to Super Tuesday. One day earlier, and meteorologists at the Storm Prediction Center notice a dangerous wind pattern, one that usually occurs in spring. They are surprised to see warm winds moving north, cool winds heading south. When they meet in Tornado Alley, the chances of tornado formation will be high. Yet tornado season is still 2 months off. Why are these 2 spring air masses meeting in winter? The answer is found in a strange ocean current 1,000 miles away in the Pacific. Joe Schaefer, the director of the Storm Prediction Center in Oklahoma, wanted to find out what caused winter tornado outbreaks.
Super Tuesday was in February. To the general public, it probably did come as rather a surprise that you're having this strong activity in February.
He begins by looking for a bigger pattern.
Newest ones are white, the oldest one.
Could the arrival of spring weather in winter be anything to do with La Niña, a vast ocean cooling event in the eastern Pacific? It's a long shot, but he knows it causes extreme weather in the most unlikely places.
There has to be some clues to what Mother Nature is really going to do.
There are always larger patterns at work. The El Niño and La Niña cycle are one of the biggest. The cycle affects vast ocean currents, which govern the warming and cooling of the oceans. The El Niño current drives east, carrying the warm waters of the tropics to the west coast of the Americas. As it does, it warms the atmosphere above it, El Nino lasts about a year. The cycle then reverses and the temperatures drop. This reversal is called La Nina. This current carries cooler seas and cooler air above. The cooler seas of a La Nina year are famous for influencing the increased strength of Atlantic hurricanes. But no one had yet proven a link to tornadoes.
We just looked at the number of tornadoes all across the country and tried to see if there was a relationship between the tornadoes and whether you were in a El Nino, La Nina, which is the opposite, or a neutral pattern, which is neither one. So we looked at those and found absolutely nothing.
Other meteorologists were also searching for a link. But weather systems are some of the most intricate patterns known to science.
People would find one thing, these people would find different conclusions. I more or less had come to the conclusion that there wasn't any link on the thing.
He couldn't believe Super Tuesday was a random event. He was convinced that there was a relationship between events like Super Tuesday and La Nina.
You always have the hope that there's some seed out there of truth, or I never would have looked at it in the first place if I really didn't think someplace in my core that there had to be some kind of relationship.
One day, Joe and his grad student have a brainstorm. Instead of counting each tornado in each year, they look only at outbreaks, days with 6 tornadoes or more. For the years they study, they find twice as many outbreaks occur in a La Nina year than they do in an El Nino year. This doesn't yet explain why the Super Tuesday outbreak occurs in winter. So they refine their search. They begin to focus only on winter tornado outbreaks. They discover that during a La Nina year, winter tornado outbreaks are likely to be more severe. 2008 was a La Nina year. The implications are enormous. Conclusive proof that the winter outbreak on Super Tuesday is caused by the La Nina effect. It's an incredible breakthrough. The mystery of how deadly winter tornado outbreaks can happen is now solved. They realize that La Nina strengthens the cool winds from the northwest, which intensifies wind shear and creates more violent tornadoes. The breakthrough is a milestone in tornado research.
Science is such that if you can actually see the relationship and prove that it exists, then you've made a contribution.
A contribution that may help forecasters save lives in the future. But the mysteries behind the Super Tuesday outbreak are far from solved. We know why it happened in winter, but what scientists now need to find out is why are they so unusually powerful? Forecaster Greg Carbon and his team are the first to spot where the trouble is brewing.
The first watches that were issued across Arkansas were to get the word out that dangerous weather is on the way. Despite the forewarning, despite the watches, and even the tornado warnings that were issued during the event, we still had loss of life.
Nothing can prepare them for the destructive power of the tornadoes they are about to see. Super Tuesday, February 5th, 2008. At 5 p.m., a giant tornado descends on Arkansas. 7 counties lie in its path. The power of this monster is about to take everyone by surprise. Using a system called the Enhanced Fujita Scale, scientists classify the strength of a twister between EF0 and EF5. EF0 can break branches from a tree. And EF2 can lift a roof off. Anything above that is rare. The vortex in an EF5 can reach 300 miles an hour, the fastest known winds on our planet. With wind speeds around 200 miles an hour, the Arkansas tornado is an EF4. And it isn't the only one. Another EF4 tornado touches down in Jackson, Tennessee, 300 miles away. It shreds Union University. Across Tennessee, 1,000 houses destroyed. 32 people killed. Debris is found 70 miles from where it was lifted. Super Tuesday's 5 EF4 twisters reveal an alarming trend. Stronger tornadoes lasting for longer. In a matter of hours, they clocked up more than a quarter of the average annual death toll. To understand why they are so destructive, scientists need to know, where is their energy coming from? Is it also connected to the powerful ocean current during La Nina? If so, how? The first clue lies 30,000 feet above the Great Plains. An invisible force traveling at 300 miles an hour is steering the storms and spinning them faster. A ribbon of wind called the jet stream. It speeds through the highest part of the sky, called the troposphere. The jet stream forms where cool air from the North Pole meets warm air from the equator. As the Earth spins, it sends the air shooting west to east at the point where the two air masses join. As polar air and Gulf air meet, the warm air is sucked up through the thunderstorms and into the troposphere, where it crashes into the jet stream. As the jet stream shoots across the United States and over the tops of the storms, it sucks on these updrafts, spinning up the storm. Just as a gust of wind across a chimney will strengthen a fire, the jet stream strengthens storms. On Super Tuesday, it's winding them up and steering them across the plains.
Here you come, Ryan. I've got the analysis, and it looks like we're starting to see moisture increase across this area and Q coming up. The watches were up. We knew that this potential existed downstream from Arkansas off to the east. It's not that the cells in Arkansas moved directly into parts of Tennessee or across the Mississippi Valley. We now had new development occurring in parts of Mississippi and Tennessee. And that new development quickly acquired supercell characteristics. And the event began to unfold quite rapidly during the evening hours.
By 5:25 that day, the jet stream hurtling across the Midwest was powering up one thundercloud after another. As the monster storms advance on Tornado Alley, some 20 million people are in their sights. When scientists look closer at the events that unfolded on Super Tuesday, they find a compelling piece of evidence that links the strength of the jet stream and the destructive force of the tornadoes to the Pacific Ocean current, La Nina. Because what Dr. Schaefer also discovers is that La Nina not only makes winter tornadoes more likely, it also makes them more powerful. During La Nina, cooler temperatures in the eastern Pacific create stronger easterly winds that make the jet stream flow faster. A faster jet stream spawns stronger tornadoes. They spin faster and track on the ground for longer. The result is more destruction. With such high speeds, the debris a powerful tornado carries can turn into missiles. a stalk of straw can fly fast enough to pierce a telephone pole.
Just hit us. It just blew all the glass out and swooped us up in the air, and next thing I know, we were flipping and flying and landed over here.
Super Tuesday 2008 was one of the worst tornado outbreaks ever. But could tragedy have been prevented? Doug Forsyth at the National Severe Storms Lab in Oklahoma has just set up a new kind of early warning radar station using technology developed by the military. Phased array radar. Traditional radar starts scanning at the bottom of a storm. By the time it gets to the top, the bottom has changed. Too slow to catch every detail of a tornado forming. But phased array radar uses multiple beams that scan in rapid succession.
To improve our lead times, we need to scan faster. With a phased array, if I can do that in less than a minute, then on the second minute, I'm already issuing the warning. So I've already increased my lead time by about four minutes. We're now getting about 13-minute lead time, which is a pretty good lead time, but we'd really like to extend that.
Phased array radar is a 2-for-1 gift. It could be the tool that leads researchers to cracking tornado genesis. And it gives forecasters more time to issue warnings. On Super Tuesday, this could have saved lives. Robin Tanamachi's team now includes a truck with phased array radar. Instead of waiting for storms to hit Doug's radar station, they can go and seek them out.
We in our radar research group feel like we're on the cutting edge using this brand new phased array technology. You get a more detailed picture of the evolution of the storm. You can watch it evolve in much greater detail.
But so far this season, that elusive tornado formation has escaped them. But buried in the data, they have discovered something just as important.
When you get a new data set and you bring it into the computer model and you start studying it, it's kind of like drinking from a fire hose. Your mind just goes off trying to think of all kinds of different things that you can do with this data set and different ways that you can analyze it and visualize it.
After feeding data from a recent storm into the software, Forsyth noticed strange patterns.
We're seeing changes go on in the storm that we've never seen before. There's some waves moving through the storm that I don't think the meteorologists knew existed, because you can't see them when you're taking snapshots between 4 and 6 minutes. You just don't see those things happening.
The brown mass is the storm. The new elements the radar reveals might just be the trigger for the tornadoes, like these waves that seem to ripple through the supercell.
Actually starting to see some new activity in storms that we've never seen before.
If they can detect the waves long enough before a twister is born, they could gain life-saving minutes.
We're going to have to do some research and see what really is happening. I think we'll put it together over the next few years and make some headway into making better warnings and at least understanding possibly this tornado genesis.
early warnings will save lives. Buried in the rubble of Super Tuesday lies another life-saving clue. Over 1,000 homes are destroyed on Super Tuesday. Research into new building design shows these losses could be avoided. It has also led to some exciting new insights into what happens within the tornadoes themselves. Investigators combing through the rubble of Super Tuesday discover a frightening truth. Tornadoes are getting more powerful. Is there anything we can do to protect ourselves? The first time wind engineer Partha Sarkar from Iowa State University surveyed the wreckage from a tornado, he was determined to do something about it.
You may survive a tornado, but your entire life is turned upside down because your whole house is gone, whole neighborhood is gone. And that's what bothers me. If you see the cars which have taken a hit from F5, you see it twisted beyond recognition, you know, people are no match for that kind of wind.
On Super Tuesday in Tennessee alone, over 500 homes are destroyed. The cost to rebuild runs into hundreds of millions. Sarkar thinks we can prevent the damage these new, more powerful tornadoes will bring.
We can do something about it. We can design these houses to at least not get completely destroyed. If it's partially destroyed, we can rebuild it. It's completely destroyed and it's gone.
In order to figure out how to protect a building, he has to know exactly what the winds are doing inside a powerful tornado. To do that, he has to make himself one. He contacts tornado expert Bill Gallus.
It was probably a phone call I'll never forget. Partha wanted to design the first wind tunnel that would create a moving tornado and wanted to discuss what ways might we use to create a moving tornado simulator.
This is the result of their collaboration. A twister in a can, 18 feet across and 11 feet high, suspended over a model target. The largest and most realistic tornado simulator ever constructed. It can recreate the same kind of tornadoes that struck on Super Tuesday, from EF1 to the more powerful EF5. It's the only simulator that can accurately measure how the wind loads of a moving tornado affect different kinds of structures.
Once they had the large simulator done and had to throw on the power switch, I think there were a lot of people waiting there and scared to death at what would happen.
In the past, wind tunnel research simulated only straight line wind. This machine reveals how the circular wind of a tornado can literally pull the roof off a house like a corkscrew. New building design will now incorporate ways to prevent this.
Every time I switch on the tornado, I feel good about it.
But this is not the only insight the machine revealed. In order for the simulator to create a tornado, they add a significant amount of downdraft. Could this be one of the elusive ingredients needed to form a real tornado? The team looked closer. Downdraft is a fast current of air passing down through the center of a rotating storm. We don't yet know how downdraft is created, only that it concentrates the storm's rotation by drawing it inward. Downdraft seems to create enough spin to produce a tornado.
It's possible that tornadoes are created in many different ways, but it seems that this particular idea of getting a downdraft that descends toward the ground almost in the shape of a circle should be something that really does lead to tornadoes.
And if tornadoes are getting more powerful, the simulator could tell us more about how they form and what the winds are capable of. But right now, scientists have a more urgent mystery to solve. It seems something else is happening to tornadoes. They're not only getting more powerful, they're not only striking outside tornado season, they're now striking outside Tornado Alley. Forecasters need to understand why. 7:15 p.m. on Super Tuesday, and Arkansas is reeling from 7 tornadoes. Tennessee is now under attack, and more storms are brewing. The team at the Storm Prediction Center can only watch.
There is a feeling of helplessness, really, at that point, because you see the violent weather unfolding. You know that there's most likely a tornado on the ground. You know that there are communities at risk. But you also know you've done just about everything you can do.
As the monster system rampages across the Upper South, it holds one more deadly surprise. Against the odds, one thundercloud crosses the Tennessee state line, moving outside Tornado Alley into Kentucky. On average, Kentucky sees 10 small tornadoes a year, mostly in the spring. It's about to be struck by 24 powerful twisters in a single night. Winter outbreaks usually occur farther south, in Arkansas and Texas, where tornadoes can feed on warmer air. What's causing them to strike so far north? This phenomenally rare event will lead them to the most chilling discovery yet. Super twisters on course for Chicago. The Super Tuesday tornado outbreak has shown that more powerful tornadoes are now striking outside their usual season. The culprit is La Nina. Its cooling effect at sea speeds up the jet stream winds over land, making winter storms spin even faster. The perfect conditions for tornadoes. But there's one last mystery. Why are tornadoes now striking further north, outside of Tornado Alley? Again, the clues lie in the events of that tragic day. 7:35 p.m. Super Tuesday.
Hey, we can see the contact point on that one. He's close. There's contact on the ground. There's debris.
Kentucky is about to be terrorized by the first of 24 twisters. A state usually considered too far north to see this many. At the Storm Prediction Center, Greg Carbon can do nothing.
When I went home that evening, I had no idea that there were already 14 fatalities. I knew we had deadly tornadoes. I knew that the day before, but the actual numbers and the actual accounts were yet to be known.
As the Super Tuesday tornadoes trespass into new territory, pushing the death toll higher, the storm too is dying. As a tornado feeds on the warm, moist inflow at ground level, the downdraft that created it keeps descending. As the cold downdraft collects at the base of the tornado, it wraps itself around the vortex and begins to cut off its warm air supply. The tornado is slowly strangled by the very force that gave it life. As the last twister retreats, the Super Tuesday storms finally run out of energy. The imbalance that created them is gone, and equilibrium is restored. But what caused the tornadoes to cross state lines? What gave them the power to move so far north, into places they are least expected? At the Carnegie Institution at Stanford in California, climate scientist Ken Caldera may have stumbled across the answer. Caldera is studying the jet stream in the hope of harnessing its power.
If we could somehow tap into this energy, it would be really incredible resource for civilization.
Caldera set out to develop an atlas showing the best places to launch wind turbines into the jet stream. As he charted the position of the jet stream from year to year, he noticed something alarming. Over the last 2 decades, the jet stream has been shifting north. As it moves, it takes severe storms along with it. This would explain why Kentucky got struck on Super Tuesday.
The jet streams act as storm tracks. They guide storms and also affect where storms are created. And so where tornadoes used to be something that was primarily of the southern areas, now we're seeing tornadoes further and further north.
But what pushes the jet stream north? For the answer, Caldera looks south. For the last 2 decades, temperatures around the equator have steadily risen. The jet stream is the boundary between tropical air and polar air. As the warm air mass around the equator expands, the polar air mass contracts. As a result, the jet stream is pushed further north. What are the odds that global warming caused Kentucky's freak outbreak?
You could think of weather as a chaotic system, a little bit like rolling dice. In the natural climate, we're rolling the dice, and every once in a while it comes up snake eyes, double ones. And you could think of climate change as loading the dice, where you should expect more snake eyes, more storms like this occurring further to the north as global warming continues. If you're living north of Tornado Alley, but you don't get any tornadoes now, you should be worried that sometime in the future, tornadoes will start showing up on your doorstep.
The jet stream is moving north over 1 mile per year. Before long, Chicago could mark the center of Tornado Alley. Scientists calculate that if a big twister tore through the city of Chicago, it could do $40 billion worth of damage and potentially kill 45,000 people. Understanding what caused the tragic events of Super Tuesday 2008 has enabled science to predict that there is worse to come. The groundbreaking discoveries about La Niña and the jet stream will go down in meteorological history.
The key, I think, for us is to not get frustrated, but to learn from these experiences and to take from them a better understanding in trying to help predict significant events in the future.
One of those significant events could be the ultimate nightmare. A super twister slamming Chicago. But by the time it strikes, we may be ready by cracking the mystery of how tornadoes form, buying enough time to warn victims of danger, and designing buildings to withstand the worst. Science could be the silver lining inside the darkest cloud. Planet Earth. 4.5 billion years of evolution. It's all going to end. Titanic forces are already at work that will destroy the world as we know it. Scientific investigators take us on an epic journey into the future of the Earth, where apocalypses will wipe out all life and destroy our planet. This is the countdown to the end of the world. $7.5 billion years from now, Earth will be consumed by fire and vaporized. But by then, it will be unrecognizable, a lifeless alien world. Long before its final moment, our planet could be struck by no less than 7 great catastrophes. One by one, they will turn the jungles into deserts, reshape the continents, and boil away the oceans. Other disasters will destroy the atmosphere, annihilate the animals, and destroy every plant. These are just the catastrophes we can predict. And what of mankind? We could be the first to go. This is the story of the death of the Earth. The first threat to life on Earth comes from the heavens. Right now, a lump of rock and metal, 6 miles wide, traveling at 17 miles per second, could be headed our way. It could strike next week, next month, or next year. But whenever it does, there will be little we can do. We would have very little warning before that threat turns into an asteroid impact. Earth has always been in the firing line.
It could happen tomorrow. It could be 100 million years from now. But it's not a matter of if, it's when.
300 million miles out from the sun, beyond Mars, is the asteroid belt, the rubble of a planet that never formed. 750,000 massive lumps of rock, more than ½ a mile across. It's an inexhaustible source of planetary ammunition that gets knocked out of the belt and sent spinning across space. NASA astronomer Professor Don Brownlee knows a lot about asteroids. The record of the devastation they bring is hard to miss.
Just look at the moon in the night. You see it's covered with craters, huge craters. Impacts that happen to all the planets that have happened for billions of years throughout our history. So this will happen.
It already has. 65 million years ago, an asteroid 6 miles wide slams into the Earth. The impact throws up millions of tons of rock thousands of feet into the air, fusing sand into glass in a split second. This one impact wipes out the dinosaurs, a species that had endured for 160 million years. So what are the odds of this kind of asteroid strike happening today? Using the visible impact record on the Moon and planets like Mars and Mercury, Brownlee has come up with an answer.
The frequency of impact of a 10-kilometer object from space, a comet or an asteroid, of the kind that wiped out the dinosaurs 65 million years ago, is on the average about 1 every 100 million years.
When it strikes, it instantly vaporizes every living thing for miles around. The sheer force of the impact buckles and cracks the Earth's crust, creating powerful earthquakes. The force of the winds whips up waves, pushing powerful tsunamis onto the land. Within a few days, the dust cloud blocks the sun, plunging the planet into freezing darkness. An endless winter that would last for more than a year. Hidden within the dust is something far worse. A sudden overdose of nitric oxide destroys 85% of the ozone layer. As the dust finally settles, the lack of ozone allows damaging ultraviolet rays to reach the surface, harming billions of people and killing plants and animals with lethal doses of radiation. By the end of that first year, at least 70% of all life would have been destroyed. Those that live underground or hibernate stand a better chance. This is what killed the dinosaurs, and one day, the same thing could happen to us. Not knowing when the next asteroid will strike makes planning difficult and worrying pointless. There is worse to come. Even if we could plan for the next catastrophe, it won't make any difference. Ice sheets several miles deep, pushing down from the poles, will be unstoppable. A global ice age is coming. How do we know? It has happened before, and one of the first clues was pulled from the La Brea tar pits. To find an ice-loving woolly mammoth was a big surprise. To find it in the heat of California was a mystery. Could California have once been covered in ice? Could it happen again? To find out, scientists need a record of changes in the climate, stretching back tens of thousands of years. It turns up in the layers of sediment at the bottom of the ocean. Marine geologist Professor Peter Domenical is searching for clues to Earth's frozen past.
It's amazing.
Deep sea sediments are really unique archives of past climate change because the sediments in the ocean accumulate very continuously and very slowly over time. So they present us with this kind of history book of past climate change.
These tiny chunks of rock in the sediment hold the answer to the USA's frozen past and to its future. Deposited 10,000 years ago, how they got here is astonishing.
Icebergs carry all these rocks and they hold them inside the iceberg and then they melt. As the iceberg melts, it drops its load. And that's how we find these big pebbles out in the middle of the ocean.
Icebergs once floated off the coast. As the bergs melted, the rocks they carried from the north sank to the seafloor. 10,000 years ago, much of North America is in the grip of an ice age. But what causes a big freeze? The answer isn't found beneath the geologists' feet, but over their heads, in outer space. The Earth orbits the Sun in an ellipse that gradually changes shape over time. The tilt of the Earth to the Sun also changes. Calculations suggested that the interaction of these changes could flip the climate from warm to cold and back again. It's called the Milankovitch cycle, after the man who discovered it. His orbital calculations showed that the Earth flipped from ice age to warmth 10,000 years ago, the exact age of the sediments Domenical has found.
It was shocking when the evidence came out that there was this very close correspondence between the astronomical calculations and then really the geologic record. People were just blown away.
But what about the future? The orbital effect is called the Milankovitch cycle because it happens over and over again.
We're well on our way, actually, into the next ice age. Something most people don't really fully appreciate. Climate was significantly warmer 5,000 and 10,000 years ago, and then we've been gradually headed into this much cooler climate.
Domenical believes the Earth will be plunged into another global ice age within 30,000 years. If the last one is anything to go by, the next will be worse. Because in the last ice age, there were just 5 million humans. Now, there are 6 billion. Could we all survive? Ice sheets 2 miles thick could cover the land. Cities like London and New York may be buried beneath thousands of feet of ice. Global sea levels could drop 400 feet as water is locked up in ice. Freezing temperatures might last 100,000 years. The food chain collapses. Plants die as they are smothered by ice. Herbivores can no longer find food and die out. As civilization collapses and food and shelter become scarce, our base survival instincts kick in. Dr. Erwin Redlener at Columbia University is an expert in how humans react to catastrophic events. The bad news is, many won't make it.
The major challenges will be to how to keep ourselves from killing each other because of a natural event like a new ice age. Enormous migrations of people trying to escape from the extreme conditions have the potential of causing a tremendous amount of deadly competition for resources, for food, for water, for power.
Billions of people could perish as vast areas of available land are swallowed by ice. But many humans will survive the big freeze in belts of green, north and south of the equator. Here, agriculture will continue, but not enough to support the billions who will now begin a battle to control it.
I think we are hardwired on a genetic DNA level to seek survival at almost any cost. And I think there's pretty good examples of that. People who were prisoners of war, and people lost in hostile environments.
In a few green areas, humans will survive, but the population will be greatly reduced. Civilization as we know it will change forever. And the next ice age is unlikely to be the last. The great ice sheets will continue to advance and retreat, devastating life and civilizations. 250 million years in the future, it gets worse. Life will face an even greater threat and be pushed to the very brink of extinction. The seas will die and the land will become desert. $250 million years in the future, having survived ice ages and perhaps even asteroid strikes, there now comes an even greater threat. The surface of the planet is completely unrecognizable. Life is being pushed to the brink of extinction. This terrifying vision of the future is caused by the same powerful forces that shape the Earth today.
Plate tectonics was one of the two major scientific advances of the 20th century. It allowed us to get an understanding that the Earth is really much more dynamic than we ever suspected.
It reveals that the Earth's surface is made up of a series of massive continental plates that are in constant motion. Where they collide, huge mountains are driven up and massive volcanoes pour out liquid rock. It shapes the face of our planet. Armed with this new information, the geological record opened up like a book, revealing that 250 million years ago, all the continents were united to form a single supercontinent we call Pangaea. This was a hot, brutal world ruled by dinosaurs. Could future movement of the tectonic plates transform the Earth once again into a single vast landmass?
We now know how the plates are moving far more accurately than ever before, and so it became tempting to look into how this might develop if we projected these motions a few million years into the future.
According to Livermore's model, 250 million years in the future, a new supercontinent will form. Africa plows into the Middle East as Antarctica and Australia fuse together. One vast landmass surrounded by a giant ocean.
We end up with a supercontinent which is primarily in the northern hemisphere and a southern hemisphere which is mainly ocean. This will give us a range of habitats within the supercontinent quite different from anything that we see at the present time.
With much of the land hundreds or thousands of miles from the ocean, rainfall becomes non-existent. No plants grow, and as the land absorbs the heat, temperatures soar. It turns to desert.
If we were looking down on the future supercontinent, what we are likely to see is something really rather like the interior of Australia.
250 million years in the future, this new world will be mostly desert, covering over half of the land, so hot and dry that few plants or animals survive. 80% of the species we see today could be wiped out. Those that do survive will have to adapt to less water, less food, and rising heat. Our distant descendants might try to take refuge in the coastal regions. But even here, there's no escaping the dangers of this new world.
Around the edges here, we're probably going to see continuing volcanism, continuing earthquakes.
The tectonic forces that push the supercontinent together are still at work. Now they begin to buckle and split the land at its weakest points. The result is massive earthquakes. Lava exploits these new cracks and bursts out, forming chains of volcanoes. Molten rock spreads over thousands of miles, incinerating every living thing in its path. Life on the land will be tough beyond our imagination, causing mass extinctions. But this is nothing compared with the devastation facing life in the new superocean. In 250 million years, a single supercontinent will dominate the face of planet Earth. It has happened before. By exploring what happened back then, we now know that this single landmass could have a devastating effect on the oceans in the future. A lethal dose of carbon dioxide may cause a mass extinction, which could wipe out 96% of life in the sea. But where will this killer carbon dioxide come from? The biggest natural CO2 producers on the planet are well known, and the supercontinent of the future will have plenty of them. Volcanoes. To understand how the carbon dioxide from volcanoes leads to mass extinction in the oceans, Dr. James Barry has been studying what happens to one particular creature called a brachiopod during similar events.
Oceans became much more acid due to all the CO2 that was released by volcanic action over 100,000 years. And that increased acidity of the ocean has caused not only brachiopods, but many other types of animal life to go extinct.
Dr. Barry is trying to understand exactly what happens when carbon dioxide levels suddenly shoot up. Among the first to feel it are shellfish.
These brachiopods are a curiosity. They're one of the earliest sort of real animal life forms that evolved on this planet. 400 million years ago, they were one of the most dominant forms of life on the planet. But they went from 30,000 species down to about 300. They're the poster child for how to go extinct.
Brachiopods had survived everything the Earth could throw at them for hundreds of millions of years. Yet it was volcanic eruptions on land that wiped out 99% of brachiopod species in the sea. Barry's research reveals how, Brachiopods are highly sensitive to carbon dioxide levels. The excess CO2 from volcanoes dissolves in the water, making it acidic.
Once it enters the ocean, it combines and reacts with seawater to form carbonic acid. And that changes the balance of chemistry in the ocean.
As the sea becomes more acidic, the brachiopods die out. In 250 million years, the hard shells of all marine invertebrates dissolve in the acidic water. As their inhabitants die, a big link in the food chain collapses. Their predators starve, and the lack of food goes right to the top of the chain. At the same time as the food chain is collapsing, another brutal consequence of a single supercontinent will be reaching its endgame. 80% of marine species live close to the coastline. With all the land locked up, there's less coast to go around. Competition for the prime real estate gets fierce. The coastline of the future supercontinent could be 70% less than it is today. So the next supercontinent will be deadly. In 250 million years, an arid desert on land and an acid ocean means a mass extinction that will make the death of the dinosaurs look like a sideshow. But amazingly, some plants, some animals will survive. Those that can adapt. Creatures like snakes and spiders that thrive in the heat. Low hardy bushes and types of cacti may be able to evolve. Life will endure for 1 billion years to come. It's only then that the final extinction of life on our planet begins. The end of all life on land. 1 billion years in the future, the world is going to get hotter. All stars, like our sun, go through a cycle of life and death. Today, the sun is middle-aged, but in 1 billion years, it will be that much closer to death. As it burns through the remainder of its fuel, internal processes will cause it to expand, bringing its surface ever closer to the Earth. The temperature will soar. It is now 86 degrees and climbing. For mankind, another 18 degrees higher, and we will have reached our physical limit. Blood thickens, strokes and organ failure follows. Sometime in the next 1 billion years, humanity will cease to function. At this point, we will have disappeared forever from the face of the Earth. But other kinds of life will be able to survive. Here at the California Academy of Sciences, Professor Lynn Rothschild searches the history of past extinctions for examples of what creatures might be able to survive in a world twice as hot as today.
What I'm holding here is an ammonite, and these were extremely successful group of invertebrates. They were wonderful predators, and they went extinct at the end of the Cretaceous. Not their fault. They were wonderful at the time, but they went.
As the sun expands and the world heats up, it all comes down to luck. If you happen just by chance to be better suited to the new world, you'll make it. If not, it's just bad luck. And in the brutally hot future Earth, we already have a fair idea who's going to be lucky.
We see animals like scorpions, like we have here, spiders, maybe some snakes that come out at night. And these are so well adapted to living in these hot, dry environments because they prevent water loss. They do everything they can to keep water inside their bodies. They stay nocturnal.
Only the most extreme adaptations can survive. But as conditions become worse, life on land heads toward its final moments. It begins with the plants. Atmospheric scientist Professor James Casting is one of only a few people in the world to have figured out what happens to the plants in 1 billion years from now. He's discovered that a drastic fall in CO2 will wipe most of them out.
CO2 will drop by a factor of 1/2. That will wipe out 95% of the plants on Earth.
Geological processes are at work today that absorb carbon dioxide and dump it in deep ocean sediments. But like all chemical processes, the higher the temperature, the faster it works. Supercharged by the hot Earth 1 billion years from now, it wipes carbon dioxide from the atmosphere.
It will drop down below the level required to sustain plant life. And that's the fundamental food source on Earth. I mean, carbon dioxide is the food of life. It's what makes photosynthesis work. And with CO2 gone, it's a very different world.
Deprived of CO2, plant life suffocates and dies. The last remnants of our green Earth turns brown and dead. One vast desert covers the land.
It's really hard to imagine a future without any plants. I guess the best way to imagine it is to go up into the desert. In a way, it's a very beautiful environment, but it is very barren, and it doesn't seem like home.
Without plants, the food chain collapses. The plant eaters starve, and their predators follow. Animals, insects, reptiles, and mammals. For life on land, everyone's luck has finally run out. There is only now one place on the entire planet that does continue to support life: the oceans.
If you think about why life both originated in the ocean and probably will be forced back into the ocean in the future, it's because the ocean is far more stable than land. If you go out into the desert in the middle of any continent here, the summers are sweltering and the winters are frozen. During that same yearly cycle, the temperature right offshore here nearly stays the same year-round.
But 1 billion years in the future, as the dying sun swells and the temperatures rise, the oceans begin to evaporate. As the water level drops, they become more and more salty. To understand what the oceans of the future will be like, Professor Rothschild has come to these salt ponds outside San Francisco, where seawater is evaporated to produce salt.
What happens here, and you'd imagine would happen on the Earth, is that as the concentration of salt goes up, 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 many of the organisms that we're familiar with, fish and kelp and algae and manta rays and so on, drop out.
It is the end for life in the oceans as we know it. Whales, dolphins, jellyfish, coral reefs, pretty much everything. All gone, unable to survive in the increasing saltiness of the water.
And at some point, you're left with brine flies, a few little worms, and some of the microbes that you see here. And at the very highest salt concentrations, about 10 times the salinity of the ocean, you only end up with organisms called halophile.
It is the halophiles, tiny organisms that thrive in high salt environments, that give the water its red color. This color is no accident.
Now, during the summer, we tend to get tanned. I've been in the pool, I look a little tanner than I would in the winter. Well, these organisms also have to protect themselves from a very strong sun, ultraviolet radiation. And so instead of tanning, they tend to produce a lot of red pigments, carotenoids. These are the same kind of compounds that you see in tomatoes and carrots and so on. And this orangey red pigment helps protect these organisms from the very high sunlight.
With a blazing sun filling the sky and temperatures rising, only these incredible survivors called extremophiles can take it. 1.2 billion years from now, all other life is gone.
As the Earth becomes a very hostile place, we're back to having a world that's only populated by microbes, very much the way it was during the early evolution of life on Earth.
Extremophiles clinging on at the ragged edge of survival in the last remnants of the ocean. The final hammer blow that will end all life is now just around the corner. 1.2 billion years from now, plants and animals have been wiped from the surface of the Earth. Only microbial extremophiles survive in a rapidly evaporating, increasingly salty ocean. For the oceans, time has finally run out. The brightness of the expanding sun boosts average global temperatures to a blistering 100 degrees, nearly double than today. Professor James Casting is investigating the devastating effect this has on the oceans of the future.
Well, we think that the Earth will start to lose its oceans when the sun gets about 10% brighter than it is today.
His findings confirm evidence gathered by Apollo astronauts in 1972. Hydrogen is escaping from the Earth. Water is made up of 1 part oxygen and 2 parts hydrogen. So what the astronauts were seeing was the infinitesimal loss of the oceans into space. Today, this amount is nothing serious, but 1.2 billion years in the future, when the temperature is 100 degrees, the process goes into overdrive. Faster evaporation now saturates the air with water. As this water rises to the top of the atmosphere, ultraviolet light from the sun splits it into its 2 component parts, oxygen and hydrogen. The hydrogen is so light, it floats off into space, lost forever. What Casting discovered was that from full to empty, the whole process of losing our oceans could take less than 200 million years. Without water, life cannot exist. So to find out when this will happen, he had to look at a planet not unlike the Earth that lost its oceans in the same way.
Well, I got interested in the future of Earth's oceans by working not on Earth, but on Venus.
Physically, Venus is almost a twin of our planet. And billions of years ago, it might have been even more similar.
May well have had liquid water on its surface at one time, just as the Earth does now. But it was too close to the sun. It lost that water by what we call a runaway greenhouse. It's likely, in my opinion, that Earth will follow the path of Venus at some point in the future.
Studying Venus helped Casting estimate when we will start to lose our oceans. The answer came as a shock.
Well, up until we had worked on this problem, many scientists thought that the Earth would retain its oceans for at least another 3 or 4 billion years. But we were able to show that bad things start to happen much earlier than that. The oceans could be lost in 1.2 billion years.
With the water gone, dry salt crusts like these are all that will remain of the Earth's magnificent oceans. Is this the end for life? Incredibly, a new discovery has shown that even without water, basic life forms can survive. But for how long?
Although we'd known that organisms could live in very high salt, we knew that they could also be trapped in solid salt. But what we didn't know is that while they're in the solid salt, it's more than them being in suspended animation, that they are actually still metabolically active. They're still breathing and eating and excreting and doing all the sorts of things they need to do, but at a very, very, very slow rate. So that was really an astounding discovery for us.
In 1.4 billion years, with the oceans finally gone, extremophiles will survive in the solid salt, but just barely.
These organisms will be able to survive a good deal longer in a salt crust like this, even in the absence of water. They won't be able to survive forever like that, but it'll buy them a little time.
Perhaps another few million years. In that time, their main protection will be the red color that acts as a sunblock. While they live, they will transform the way our planet looks from space.
People always think of the Earth as this beautiful blue planet, you know, the pale blue dot in the sky. But the fact is, for almost half of Earth's future history, it will be a Barbie planet. It will be covered with pink salt.
This is the Earth 1.4 billion years from now. The extremophiles cling on in an increasingly desperate fight, but the rising temperatures as the sun brightens eventually defeat them. By 1.6 billion years into the future, the temperature has climbed to 224 degrees, far above the boiling point of water. Life finally loses the battle. The last remaining extremophile dies.
There are several poignant moments in geologic history. The Earth losing its oceans will be the most poignant of all, because that really will be the end of life as we know it. And unless we've figured out how to colonize other planets, then life will come to an end. It's a pretty sobering thought.
The time of the pink Earth passes. Our planet is reduced to a brown, featureless world. Unless we have found a foothold on another, this is the end of life in our universe. For the next 6 billion years, our dead world orbits the dying sun. Only an astronomer can see this far into the future, to the Earth's final moment of existence. Dr. Robert Smith from the University of Sussex has unraveled the Earth's ultimate fate. But his journey of discovery has taken some unexpected twists and turns. The process begins as the dying sun continues to swell in size.
The sun getting bigger will have severe consequences for the Earth, because we predict that the sun will get at least 200 times its present size.
All stars go through a cycle of life and death. Astronomers know this because they can see stars that represent every stage of life that our sun will go through. In 7 billion years, our sun will be close to death. The sun is now 1,000 times brighter, 200 times its present size, and still growing. The heat literally dissolves the face of the Earth, wiping away the last of its uniqueness.
As the sun gets bigger, the mountains will start to melt, and instead of having high mountains and deep ocean depths, everything will flow into a uniform sphere, be featureless, and very, very hot.
Earth's surface is now melting in 2,500 degree heat. The surface runs with liquid metal. Our planet is utterly unrecognizable, a totally alien world. The end is now close. But Dr. Smith's calculations revealed a last-minute escape might just be possible. $7.5 billion years in the future. The mountains and oceans have been erased from the Earth's surface. The temperature is over 2,500 degrees. It has been lifeless for 6 billion years. Now the Earth itself is about to die. At the heart of the dying sun, helium is reaching a critical stage. It's becoming so dense, its atoms so crowded, that the core is becoming explosively unstable. It now takes on its final form, a red giant, 256 times bigger than it is now. It fills the sky.
First of all, you would see the size of the sun beginning to increase. It would get redder, it would get brighter. At the moment, we're used to seeing it about the size of the full moon. Then it would get bigger and bigger, it would fill more and more of the sky, till eventually when it became a red giant, it would probably fill something like half the sky.
As the sun burns up the last of its fuel, it expands outwards. Now almost 200 million miles in diameter and swallowing everything in its path. Is this the fate of planet Earth? When Dr. Smith first tried to find out, the figures showed that as the sun gets bigger, it loses its gravitational grip on the Earth. The chain is broken, and our planet drifts off into space, potentially escaping a fiery death. It seemed that Smith had saved the planet.
It was a good feeling that we'd saved the Earth, and indeed some of the newspaper headlines said exactly that.
But then one of Smith's colleagues took another look and produced new calculations about the red giant. These seemed to suggest a radically different picture.
When we came to look at the calculations again, we realized that we'd missed something out. We realized that there was a missing effect which we had to take into account, and that's to do with tides.
What they hadn't taken into account are the tidal effects of the Earth on the sun. The Earth's gravity will create a tidal bulge on the surface of the sun, in much the same way as the moon affects the rise of the ocean tides on Earth today. This bulge, in turn, creates a drag on the Earth, pulling it back towards the sun. Smith set to work using the new data to find out just what would happen now.
We didn't know what to expect when we first put in this additional effect. We hoped that even when we put in the tides, the Earth would still escape.
Smith announced a very different set of results. The news was bad. The tidal effect chains the Earth to the sun.
When we came to look at this problem again and put in the extra effects and realized that the Earth would in fact not survive, we decided to call our paper Doomsday.
The surface of the Earth is now nearly 2,500 degrees, hot enough to melt metal. The outer fringes of the sun reach out to engulf the Earth.
We try to imagine what it would look like to see the Earth disappearing. Just be like an asteroid crashing through this Earth's atmosphere. It will burn up completely. It will vaporize, it will disappear, it will become part of the sun, and it will be as if it has never been.
12 billion years of planetary history ends. The death of planet Earth, engulfed in flame, vaporized by the sun, reduced to atoms.
Sort of dust to dust. But it's not such a bad fate, because those atoms, your dog's atoms, your car's atoms, they go out into space, and what do? They end up forming new stars, new planets, and maybe even new people.
It's a cruel act of fate that life-giving stars will one day go bad. Big changes are coming. By understanding how Earth worked in the past and how it works today, science is beginning to understand what the future may bring. The death of the Earth is already laid out in front of us. It's written into its geological past, and literally into the stars above us.